Hello, this is Concrete Path and the final lecture for influence line diagrams. And this one would be shortcuts to get the influence line diagrams for your members of the truss. Let's go one by one. Let's take the first kind of truss that we call as truss, Warren truss. Okay, Warren truss. And you need to get the ILD for the members. We say member one, that's CD. After that, you need to get QR, PC, QC, PA. Okay, these members we had to get. Let's take the first one, that's CD. So for the CD, I would say this one. So how can you draw this one? So we say this is the bottom member, bottom chord member. So let's say that we have bottom chord members in the truss. We have bottom chord members, bottom members, and we have upper chord members, upper chord members. They are in this way, horizontal. They are horizontal members. And one more is that we may be having diagonal members, web members. They are diagonal members, web members. So they are in this fashion, or they can be in this fashion. And one is that end diagonal. One is that end diagonal, the end one. So end one may be in this way, or it can be in this way, like that of PA. Let's say this is PA. And one more can be there. That's vertical. The member can be vertical also in this fashion. That it can be vertical also. So we have different kinds of members. So for the CD, that we say this is a bottom chord member. CD, we say this is a bottom chord member. And the case is that loading is a deck type loading. And let's take the case of loading, that we say loading is deck type. If the loading is deck type loading, that means the joints that are going to be having the loading, that are P, Q, R, and this one and this one. So these are the loading joints, not the ABC, not the A, C, D, B, etc. But the loading joints from the top, we are applying the loads on those joints. So let's have that CD member. Let's have that CD member here. So if we have a member CD, that's a horizontal member, or we can say that's a bottom chord member, and we have to check that what is the triangle it's in which triangle it's having this CD. So we say that CD is having in this triangle of CDQ, CDQ. Then once we got that triangle in which the member is, then we see on what joint the loading is there, on what joint the loading is there. So for we say that the loading is on the joint Q. So that means we have only one critical point in the what you call as ILD, that's at point Q, and rest you have to join with the support A and support B by a straight line. Let's have that first one. Let's say let's go for the ILD for CD, ILD for CD, ILD for CD, ILD for CD. So I would say loading is from the top. That means loading joint is Q. So our critical point is only one. That's point Q, and we say the diagram, influence line diagram, would be a straight line between those. That is, you have to join the critical point with the ends by a straight line. So this is the ILD for CD. Finally, I would say the value here is equals to, let's say this is value of A and this is value of B. So I would say this value ordinate equals to AB by L, and this is the ordinate. Actually, if you have bending BMD, if you have that simply support beam, you want to get bending moment at any section C, we say that the ordinate here is AB by L. But we are talking about the force in the member. That means you have to divide by that H. So if you divide by that height of H, let's say the height here is H, small h, so you have the ordinate of AB by L, and you have this divide of H also. So this is AB by L divided by H. Now you want to say whether this is positive or negative, so I would say if the bottom member is there, so CD is the bottom chord member, so for that we say we have tensile positive ILD. Let's finalize that. If you have a, so these are the rules for drawing these shortcuts. So I would say for the bottom chord member, if you have a bottom member, that's horizontal. Okay, you take that triangle on which you take that particular triangle in which that member is. This is our member, and you want to see what is the which triangle it's having, and then you finally see what are the loading joints we can have. If this is a loading joint, that means peak at the joint, peak at the other joint, peak at other joint also. Only one joint is formed for the bottom members, other joint. So let's take this one. Okay. Then whether so bottom chord members are subjected to tensile ILD. So we say that positive ILD you have to draw positive ILD with the ordinate of AB by L H, AB by L H, and A and B is with respect to the point where we have peak. Okay. Now second one is that you have to get for the QR. QR is the top member. Is QR top member? I would say QR is the top member. So QR is the top member. So if I draw reference line for the ILD, QR is the top member, and for the top member you have to draw tensile. You have to draw compressive. So for the top member you have to draw that compressive. So the Q member, let's write that. If you have upper chord member, that's so you have to write for the top or upper members. If there is an upper member or top chord member, for that you have to see if there is some member in this way, we have to see the triangle. And where is the loading joints? I would say loading joints, we have two loading joints, and accordingly we can get the diagram. We can get the diagram accordingly. So we have that negative ILD with ordinates in this way, that the diagram would be that AB by L. Now we have to see whether our ordinate, whether the peak is having the loading or not. So we have different possibilities here. Let's talk about this one, QR. Let's talk about QR. We will see here. If you're talking about QR, I would say what is the triangle we are having in the QR? What is the triangle we are having in the QR? I would say QR is this one. This one is our QR. And I would say, what are the loading joints for the QR? Is it having this loading joint or the other two? What are the loading joints for the deck type loading? Which are the joints which are which out of these three, which are the loading joints? I would say loading joint is this one and this one. That's Q and R. That means this one is not the this one is not the peak. It would have been peak if the loading was at this joint, but I would say loading is not at the joint, but peak would be there. But the thing is that actually loading is not there, so we don't have to get the actual peak there. So let's have that now. I would say peak should have been at the point D. So peak should have been at the point D from the triangle. I would say peak should have been here at the point D, but because loading is only applied at Q and R, that means there would be two peaks developed at Q and R. Some values would be there. Then finally, I would say you have to join those two critical points. Then after that, you have to join them also. By this way. There would be some value here that would be solved by similar triangles. I would say this ordinate would have been AB by L H. If we extend this one and if I extend this one, so this ordinate would have been AB by L into H, where your A value is equals to AD. So A equals to AD and B equals to DB. D equals to DB. So finally, I would have written that AB by LH, but the thing is that loading joints are only at the point Q and R, not at the D. So our peak developed would be here and here. This is not the actual peak. So our peak actual is in this fashion. So this is our ordinates for this ILD. So, and this is negative because if the member is, we call it as top chord member, for that you have to draw ILD in that as negative ILD. So your negative ILD. So for the top chord member, you have to see whether your loading joint is how many loading joints we have. Accordingly, we have that number of peaks. Since in this case loading joints are 2 and the member is itself that one, so we say peaks would get developed here and here, but it should have a maximum ordinate here corresponding to the other third joint of the triangle. But because it's what you call as loading or is not applied at that joint, so our diagram looks like in this fashion. This is our loading that ILD. Let's have third one. PC. PC is a diagonal member. You see, PC is a diagonal member. Is PC a diagonal member? So you see, why is the PC? I would say PC is a diagonal member. Let's talk about PC. Why is the PC? This is the PC. So PC is a diagonal member. If I take this element, if I take this member, I'm saying what is the triangle we are having associated with this. How many triangles we have associated with this? I would say one of the triangle is this one, and one more triangle, that's PQC. If this was your PC, we have two triangles. Now we need to get the loading joints. Where are the loading joints available? I would say one of the loading joint is this one, and one of the loading joint is this one. Okay, so there we have two loading joints. We have two different loading joints. PC web diagonal web members. Now the thing is that we say you take the triangle, okay, and then we say the P gets developed at this location, and this is A by L, and this is A by L, D by H, A by L, D by H. Okay, okay. So we got that. We are saying that which out of these joints, four joints we are having. We say which are the two which are having loading. Which joints are having the loading? I would say one of the joint is P and one of the joint is Q that are having the loading. So our critical ordinates or points would be that P and Q in the ILD. Let's have that. Let's have those two in the ILD. That we have two critical points for the ILD. That means two critical points for the ILD. You write it in the side, two critical points for the ILD for this member PC. For this member PC, you have two critical points for the ILD. Now, how can you draw the ILD? So we say that let's write it again. That's general rule, that shortcut rules. So for the top and bottom chord members, we have the diagram of that ILD as that of a BMD, that ILD for BMD at any section. So this is the ILD for top or bottom chord members. Then we see that whether it is positive or negative, and the ordinate is AB by LH, AB by LH. Then similarly for the, now if we have diagonal members, for the diagonal members, our diagram is some sort of, it should have been some sort of SFD, ILD for shear force at any section. But based on that, we say because it's a truss member and we have joints, and accordingly if there are two critical joints, if this is one joint and one more joint is there, we don't have the diagram in this fashion. We say we have this joint and one more joint is here, so accordingly we got these two different values. Then we join these two by a straight line. So this is our ILD. So from one of the critical point we have ILD downwards, and one of the critical side we have ILD upwards. That can be vice versa also. So this is the general diagram for the ILD related to diagonal members. So this one. And for the bottom and top members, we have diagram of some sort of in this fashion. That is some sort of AB by L, but you have to divide by that H also. And similarly here the value should have been, if this was your that ILD for your shear at any section C, I would say this value was equals to A by L, and this was equals to B by L. Similarly, we say that this value is equals to X by L, and you have to multiply that factor of D by H, D by H factor. And for this one, we would say this value should be equals to B by L into D by H, this factor of D by H. And then we see whether this is negative or positive. That's the trick here, what we see here. That's what the trick's all about. That. So for the member PC, see in which direction. So what's the orientation of PC? Is it in this way or is it in this way? I would say PC is in this way. PC is in this way. So I have to keep this. I have to assume that this is the PC. Let's have that. I have to assume that this is some PC. This is some PC. I have to place it such a way that that it touches the origin point. How can you place it? How can you assume that this is some point P and there is some point C? How can you touch that point P to the origin and then have that line PC? That means the point C should be somewhere downwards. So this should be the direction. So I would say the direction for that ILD would be some same sort of in the same sort of nature. Let's say the ordinate, we have the critical location. What we derived the critical location. We say one of the critical location is point P and one of the critical location is Q. So if the point P is the critical location, that means up to the point P we have one ordinate that's critical. So up to the point P we have critical location, and after that we have point Q, that's one more critical point. That's one more critical point. So we only have two critical points. Once you got the two critical points, you join them by a straight line, and then you connect them to the ends such that you make an ILD. So we got the two critical points. Now we don't know whether our first peak coordinate is above the line, that's positive, or below the line, that is negative. So for that, you take the member PC in the same way and connect it at the starting point A. Then you see the PA is going downwards. So PC is going downwards. So I would say your diagram would be some sort of this one. So this is your ordinate number one. That means second ordinate would be at the top from the other side. That means next ordinate would be somewhere here, and then I can join that ordinate with the end line, that's point B. So this is your aldehyde. Then finally you join these two also. Now I would say, what is the value we can have here? What is this value equals to? So I would say this value is equals to some length of a by 2, maybe a by 2, maybe a by 2. Let's say this is some a by 2, or we can say this is some x value of a by 2. Then finally I would say this ordinate is equals to xd by l h, xd by lh, where your value of x is towards the negative side of x-axis. Let's say that xd by lh. And for this ordinate, I would say you have to go to this much, that's your x, and this is your ordinate of this ordinate equals to xd by lh, xd by lh. That's also equals to xd by cosecant, x by l of cosecant theta, x by l of cosecant theta. So once we said that, I would say this is your negative side, this is your positive side of the ILD, negative positive side. Let's take the fourth case, that's your member QC. Member QC. Now we are going to see member QC. Let's remove this now. We are going to take member QC, member QC, member QC, member QC. Member QC. You check where is the member QC. I would say this is the member QC, and take it out and just see that which of those triangles we are having with the member QC. I would say one of the triangle is QCD. If this is Q, we say this is your one of the triangle QCD, and one of the more triangle we have PQC, PQC. So I would say how many triangles are connected with this member QC? I would say two triangles. Then I would say, where is the loading? Is the loading deck type or it's through type? I would say loading is deck type. That means what are the loading joints we have? What are the loading joints we have? I would say your joint P and joint Q is your loading points. So these 2 points are your loading points. That means the same as that of the previous problem, that PC. So loading joints are same. That means one of the critical location would be at the point P, and one of the critical ordinate would be at point Q. Then only we need to have a reference line. We need to have a reference line. I would say whether our first ordinate is the negative or positive, whether the first ordinate is in this way or whether it's in this way. Once I got the first ordinate, then accordingly second ordinate would be in the opposite, that it would be above or below with respect to the reference line. It would be in the opposite manner. So the first thing is that you have to check the member. What is the orientation of the member? I would say your member is some sort of QC is in this way. So let's say this is some C and this is some Q. So firstly, which of the points starts with respect to A? I would say point C is closer to point Q. Point C is closer than point Q with respect to A. So you have to keep the point C at the point A location in the ILD. Then you see whether how is the orientation of C and Q. So that's in this way. So your diagram starting would be in this way. This is your starting of the diagram. So I would say your diagram would be some sort of initial portion would be in this fashion up to this line, and second part would be definitely below this reference line somewhere here, such that it touches to touches the point B by a linear fashion. Then after that we have to join those 2 points also by a straight line. So I would say this value is equals to some x value here. I don't know the value of x, so you just see what is the value of x up to the point B. So that's x, some d by lh, and this one is also x d by lh, where your value of x is in this direction, x value. So this x value is equals to, here the x value equals to some qb, and for this one x was equals to a p. So this one is your positive and this one is your negative diagram. So this was your ILD for the diagonal members. Do we have any other thing? Member PA. So this one is also member PA. Member PA is also diagonal member, but the difference is that it's not inside, it's not internal diagonal member, it's the end diagonal. We call it as end diagonal. So your member PA, it's end diagonal. So there is a difference between the internal diagonals, internal members, internal web members, and the external web member. So let's take that element. Let's take the member PA. So this is some PA. You see how many triangles we have associated with the member PA? I would say only one. That's PAC. So this is the difference between internal diagonal members and the external diagonal members. That's the end diagonal. I would say in this one we have only one triangle associated, but the internal, you take any internal member, internal diagonal member, we have two triangles associated with that. So accordingly, your that means we had two peaks in the ILD for diagonal members, but in this but in the end diagonal we might be having only one peak coordinate maybe. So let's check that. I would say, which of these is the loading joint? Because of the deck type loading, I would say only one of the joint is having loading. So point P is the critical one. Point P is only the one that's a critical point. So point P is only the critical location. So that means you have to join the line. You have this line, and there would be some point. There would be one point which is critical. I don't know the value, whether it's positive or negative. That I have to check. I would say you have the orientation of PA in this way. I would say the orientation of PA. That's the orientation of PA. So I would take this point A at this location. Then I have to place this PA. How can you place this point P, this line PA? How can you place this line PA? How can you place this line PA? That means the diagram, initial part of the diagram would be in this fashion. Initial part of the diagram would be in this fashion. Is it true? Is it true? Is it true? So this is an exceptional case of the problem. This is an exceptional case of the problem. So we got only one critical ordinate. That would be at the location of point P. We already got that, but we don't know whether the value would be here or whether the value is here. So, but we say that the value is not positive. The value is not, first part is not positive, but it's negative. So we say, how can you justify it? How can you justify it? I would say that let's analyze it. Let's analyze this case. This is a different case because it is an end diagonal, and the loading is, we would see what's the difference here. What's the critical thing for this case? This is the end diagonal, and there is some exception here for this case. Let's have that. I would analyze this one. So I would say this is a member PA. We have this member PA, and if I cut this section somewhere here, I would say you have a support here, and you are applying some load at the joint P. If you apply load at joint P, I want to analyze the value. What's the value we can have when load was at P? I want to analyze because I have only one critical point. I have only one critical point here. If I got the one critical point based on the triangle, I said that there is only one critical point. If I got the one critical point, then I can make the diagram. The diagram would be some sort of triangle, for this member, diagonal member also. Even for the diagonal member, I can get the triangle variation. So let's analyze this one. This is that exceptional case, or this is a different case from with respect to the shortcuts we have made. Let's take this one. So if I apply the load at joint P, let me apply the load at joint P for this case. If I apply the load at joint P, what would be the reaction here? Can you get the reaction here? Can you get the reaction? If the total length is, let's say total length is, how many panels we have? 1, 2, 3, 4, 5. 5 panels we have. And what is this length? Is it 0.5? 0.5 of A. So the reaction would be 4.5 divided by 5. Would that be reaction equals to 4.5 by 5? So if the reaction is 4.5 by 5, let's have that reaction here. I would say the reaction here is 4.5 by 5. And if I cut the section, I want the force in this member. So I would say you are applying 4.5 by 5 reaction here, and there is some component here. It might be having some force F. I would say the force F would be compressive. Would that be compressive? Force F would be compressive or negative, tensile? both are in the same direction. That means the arrow is assumed. That's not correct. That the arrow should be towards the joint. That's compressed. So that's minus 4.5 by 5, but with sine component, sine theta. There is some theta. So finally you would get a value of cosecant theta also here. So minus 4.5 by 5 cosecant theta. That's, see what is the difference here. Let's have that. So I would say the ordinate here is negative with a value of 4.5 by 5 cosecant theta. That's also equals to x by L, but with some factor of d by h. What can you tell me? What is this value of x? This value of x is actually 4.5, but where from where side this 4.5 should be? So the value of x should be in this direction. So this should be the direction of x. So that means it is the second ordinate with respect to the, if you keep that in the mind that we had two ordinates for the diagonal member. One of the ordinate is above the line, and one of the ordinate is below the line. And we said that, because we said that if you analyze this member, you will say the diagram would be, if I show the orientation of this member PA, that would be some sort of, the diagram would be formed in this way. But that's not the case here. That shortcut was violated when we had two triangles. Let's say if we had two triangles. We got the value now. Finally, we got the value that the ordinate P coordinate is that 4.5 by L cosecant theta. That's x by L d by h, and the value of x is also 4.5. X is equals to 4.5 of A, and L is equals to 5A. So you got that. Okay. Now let's remove this and get a clear picture, more clear picture. Okay. I would say, can you get the reaction? Can you get the value of PA when, since you are not applying load at the joint A, you are applying load only on the top members. How can you apply the load just here? If the load was just at the point level, at the level of A, let's have that one also. If the load was at this location, how can you apply the load at this location when there is no member, when there is no any other member? Because your truss starts from point P, and you have to see what is the value of P A member force when load was just above point A. That's when it was just above the support reaction A. So we say there would be one more triangle. There would be one more triangle somewhere here. If I have one more triangle somewhere here, that we can call as approach span. This part we can call as approach span. If I call it as approach span, then if I analyze that part also, I would say there we have, for the member PA, we have two triangles. One is your real triangle, and next one is that approach triangle, and we can say fake triangle. And then I would say, what are the loading joints we can have? I would say one of the loading joint would be here, and one of the loading joint would be here. Let's say this is some O. That's some imaginary span, imaginary triangle, or we can call it as approach span. From the side we are having some road, and this is your bridge. Okay. Then if I apply the load here, and if I apply the load here, because they are deck type loading, that means one of the ordinate would be developed here, and one of the ordinate would be developed here. So if I say that I got one of the ordinates, so I would say, what should be the diagram now? What should be the final diagram looks like? I would say the diagram would have been, because your member is PA, the diagram should start in this direction. If I try to start that diagram in this direction, then I would say the second ordinate would be somewhere at the point B. Then I had to join that in this fashion also. I would say one of the ordinate, because the origin O is the starting point itself. It's the starting point itself. Then how can you draw these two? Because I would say there is no, this part was not actually there, so this part won't be there. So how can you join now if this part is not there? If this part is not there, and this line is also then finally not there, that means the line should be some dashed line up to the support A. Then after that I have to join that by a straight line. So the actual diagram is in this fashion for this one. So this is a very exceptional case for the short tricks. By the analysis, you can directly solve it. If you watch the previous lecture, we perform analysis, we cut the section and analyze each and every loading point. Then we can draw the diagram that would be in this fashion. That means up to this point we can have diagram. This is the actual length of 5A. This was extra length of approach span of length A. This was some extra. This was outside the truss. Your truss starts from this point only. So so the actual diagram would be only this part. This would be actual diagram. You can have that analysis also if you perform the analysis. So this is out of the short tricks, we can say, a little bit from outside the short tricks. But we one thing we know, that once we got the PA, I would say there was only one triangle, and the loading joint was this one, and this was the critical location for the ordinate, P coordinate. So one of the P coordinates would have been developed at this location. So I would say the diagram would be now in this fashion. So a P coordinate of 4.5 by 5 cosecant theta. This is the ordinate we can have. If I have the line now, I would say one of the ordinates was negative 4.5 cosecant theta. Then I have to join it to the end point, and from this side I don't have to connect it with this line. I don't have to connect it with this line. I have to think that there was some imaginary one more. There was one more imaginary span, imaginary length of A. There was some imaginary length of, if this was A by 2, this is also A by 2, such that the point O is somewhere here. Then I would have to join that by a straight line. But actually the span is up to the point A by 2, so I have to connect it in this fashion. So this is the actual diagram. So the actual diagram is in this way, that this is the actual diagram. Actually, this is the actual diagram we have. Only one P coordinate. Okay, this is the end of the problem. Let's take the second case. That's same truss, but loading is not on the deck type. Loading is not deck type, but loading is through type. Let's see this member PA also in that case. Let's see this member also in that case. PA also. We are going to see this member PA in that case also. Let's have the loading now. For the same truss, we are going to see the loading for the through type loading. For the loading is through type. If the loading is through type, let's have the same truss for the loading when the loading is through type. When the loading is through type. 1 2 3 4 1 2 3 4 5 1 2 3 4 5. All members are of equal length. Let's say that this is A, this is B, and length L is equals to 5A. L equals to 5A, and there we have PQR, ABC, ABCD, and loading is through type. That means loading joints are, what are the loading joints? So these are the loading joints, A, C, D. These are the loading joints we have. Now let's go for the first case, that's CD. Let's draw the ILD for CD. ILD for CD. For the CD, you have to see where is the CD actually. I would say CD is the bottom chord member. Do you know what's the trick we had for the bottom chord members? And its diagram is some sort of that ILD for bending moment at any section. That triangle, some sort of triangle is there, and we need to get this triangle. Let's keep the first. Let's go for the first that. Let's analyze it. Let's analyze it first. I would say you have this member CD. This is your member CD. Then you find the triangle. Where is the triangle? Which triangle is your CD is having? I would say CD is having the triangle of CDQ. So this is the triangle we are having. And then after that we say, where are the loading joints? Where are the loading joints we have? I would say the loading joint is this one, and the loading joint is this one. That means two peak coordinates. Two peak coordinates would be there. Let's take the diagram. And whether this is positive or negative, we say for the bottom members, we said this is diagram is positive. Bottom members diagram positive, ILD positive. ILD is positive for the bottom members. So I would say one of the critical point is at the location of C, one of the one more critical point is at the location of D. So then finally join them by a straight line. So this is the diagram of, this is the ILD we have. So these two values can be different. This value is equals to, here the slope would be something, but I would say one thing, that if the loading joint was Q, if the loading joint was Q, peak would have been at the location of Q. So, but because the loading is not at the joint Q, so I should have this point Q somewhere here. But I should not have this one as actual variation. So this is not the actual variation. That means then finally I have to join them by a straight line, because we are applying loads only at the joints C and D. We are not applying load at the Q. So this value would have been, this peak ordinate, actual peak ordinate, which is bigger, this would have been equals to AB by LH. If this was A, if this was equals to A and this was B, this was equals to B, then I would say the peak ordinate would have been AB by LH, but because loading joints are only C and D, that means the ordinates, actual ordinates would be, your actual peak ordinates are only C and D, which are having some value. You can get that value by symmetric triangles. You can get that value by symmetric triangles, and that's easy to calculate. And this is a positive diagram for bottom members. Hope you enjoyed that. Hope you got it. Okay, let's take the second member. That's what we call as QR. Let's take the QR. That's a top chord member, QR. So QR is the top chord member. Let's take this triangle QR, and which is it's having only one triangle associated with that member QR. We are having only one triangle, that's QRD. So I would say, what is the loading joint we have? Because of the through type loading, we said the loading joint is only D. So that means only one peak ordinate. Let's go for that one peak ordinate, and that at the location of D. So if I make that ILD, I would say your peak ordinate is only 1. Now I have to see whether the diagram would be positive or negative. Since your QR is a top chord member, for that we draw negative ILD, that's compressive ILD, that's negative ILD. Let's have that ILD negative. And peak ordinate, I have to ensure that peak ordinate is at the location of D. So we got the critical location where the peak ordinate would be. Now we say that the diagram is negative, so below the reference line, and we say the ordinate value was this value is equals to AB by LH. This peak ordinate is equals to AB by LH, where your A value is this one and B value is this one. AB by LH, this is your negative ILD for QR. Some sort of ILD for any bending moment at any section. Some sort of that. Okay. Let's go for the third case. Let's take the third one. That's your member QC. For the QC member, which is your QC member? So QC member is, this is your QC member. Let's take this triangle. Let's take this member QC. Then I would say, what are the triangles associated with that QC? If this is QC, what are the triangles associated with that QC member? I would say one of the triangle is QCD, one of the triangle is PQC, one of the triangle is PQC. Now I would say, what are the loading joints we have? Because of the through type loading, what are the loading joints we have out of these? I would say loading joint C is there, loading joint D is there. Loading joint C and loading joint D is there. So we know that for the diagonal members, your diagram is some sort of ILD for shear force at any section, some sort of this way, XD by LH, and one of the side is negative, one of the side is positive. Now we have to see whether our diagram is positive or negative. Okay, so we got the two critical points. One of the coordinate is at point C, one of the critical coordinate is at point C, and one of the critical ordinate is at point D. So we got the locations. Now we need to say whether our starting diagram is above the line or it is below the line. Let's take that one also. I would say your member orientation is in this way. So I had to, our diagram would start in this way. Our diagram would start in this way, such that, such that, such that, such that. I would say the diagram would be, this is your diagram. Based on the orientation of CD, so your diagonal is a function of orientation. Let's have that. Orientation. QC orientation is in this way. So start it by the same orientation. So this is the direction. Once we got the one of the ordinates, and second ordinate would be somewhere here, that then we join it with the point B. So finally these two ordinates are also joined by a straight line. So this is your ILD for the member, what you call as QC. ILD for member QC. That means if the load is, when the load was at this location, you had a member force in the you had a force in the member QC that's equals to some ordinate of this one, and that's negative. That means if force of 100 kilonewton was there, so I had some ordinate here Z. So force in the member QC was F times Z. This was the value, negative times compressive. Okay, let's get that now. Okay, this is your ILD. Now I would say, what are the values we can have? What are the ordinate values we have? I would say this value is equals to XD by LH, where your value of X is this AC. X equals to AC. And for this one, I would say this is also XD by LH, and your value of X equals to some dB. X equals to dB. Okay, this is your positive. From the top we have positive, and this one is negative. Let's take the third. Let's take one more case. That's in the member. Which of the member is we are left with? I would say, which of the member we are left with? The member QD. Let's take the reference line. QD. Which of these is QD? I would say the QD is this one. So this is our QD. Let's have that QD. How many triangles we have associated with that QD? So I would say 2 triangles. One is your QRD, and one more triangle is that we have, that we can call as QCD. Now we need to get the loading joints. What are the loading joints we have? I would say one of the loading joint is C because of the through type loading, and one joint is D. So we got the two critical locations. One is the location of C, and one is the location of D. Now we need to get whether our starting would be downwards or it would be upwards. So for that you have to see what is the orientation of QD. What is the orientation of QD? Orientation of QD is in this direction. That means the starting of the diagram would be in this way, and from the other side would be having some value, from the other side some value, then you join that also. So finally diagram would be in this fashion. So this ordinate would be equals to some X value here, that's AC. I would say that ordinate would be XD by LH. That's some value of X by L cosecant theta. And from this side, we'd say there is some value of X, and I would say there is some XD by LH ordinate, positive, negative. Let's take the case that's PA. Let's take the case of PA. I would say there's some reference line, and let's get the PA member. Let's take the PA member. I would say this is the PA member. Then I would say how many triangles we have associated with the member N diagonal. That's N diagonal. Member PA is the N diagonal. How many triangles we have associated with this member? I would say only one triangle. That's PAC. And I would finally say how many loading joints we have. I would say one of the joint is A, one of the joint is C. That's because of the through type loading. I would say loading joint can be A, loading joint can be C. That means we can have two critical locations. We can have two critical locations. One at A, one at C. One at A, one at C. Now we would say, okay, we have one critical location here. We have one more critical location here. Then I would say what's the value? So how should we start it? Then I would say whether our first ordinate is above the line or below the line. Then for that for that, since it's some sort of previous case, if I say our start would be in this fashion, then how we got the next critical point? How can you get the next critical point? It should have been somewhere here. But it's not possible. It's not possible. It's not possible diagram for that. Then we say that there would be some approach span also for this case also. There would be some approach span also. Because it is the end diagonal, you have to make the approach span also for this case. If I make the approach span also, let's say there was one more triangle here. There was one more triangle here. And the loading joint was only P. Loading joint was A and loading joint was C. Loading joint was A and loading joint was C. Now from this reference line, I have one ordinate. That's one critical location is this one and one critical location is this one. Now if I say your direction would be in this fashion, your starting would be in this fashion, then from the other side your direction would be some critical value here also, and then finally you join it with the endpoint B. So your diagram would have been in this fashion. Some sort of diagram would have been in this fashion. Okay, but the thing is that when we apply, now we want to see whether this should have been case or not. Let's analyze one of the case, that is the first case, that when the load, if I analyze for the case when load was at joint A, if I analyze this point, and I can directly finally get one, I would say one of the critical location is at C. That's definite. And from this case I would say that's negative side. That's definite yet that point C would be there from the negative side with the ordinate of xd by LH. Now I want to see whether the diagram for the first case would be in this way, some sort of in this way, or it would be some sort of in this way. Now for that we need to get the ordinate at when the load was at just point A. I need to get that ordinate. Once I got that ordinate, then I can finally say what's the diagram nature looks like. One thing is for sure, based on this trick that we said, what is the triangle we have? I said your triangle PAC. Then I said loading joints are A and C. That means two critical points are there. One is A and one is C. I got one critical location of C. Now if you want to get the location of A, let's get for that. I would be taking load for that. I would be taking this section. Let's take the section. This was the section. I would say you are applying load. Just add the load at the support A itself. If you are applying a unit load at this joint A, there is some reaction of 1 also there, and there is some force in the member A, F, PA, and there is some horizontal force also. I would say by summation Fy equals to 0. What is this F PA equals to? That's some value of 0 and some cosecant theta. 0 cosecant theta. Is that 0? That means the peak ordinate at point A, that's 0. So the final variation would be in this fashion. Final variation would be in this fashion. So we can also write for this one. We can write this value ordinate as equals to xd by LH, where your x value equals to 0. So finally this is also 0. This is xd by LH. And one more thing is that if you try to extend this line, you would get this ordinate. This is not actual value, but the ordinate here would have been equals to L by L d by h. That's d by h. That's the ordinate of d by h. It would have been a value of d by h. So we got the difference between the previous case when loading joint was from the top. When the loading joint was P, deck type loading, the diagram for the PA was in this way. That some sort of in this way. Diagram was in this way. This was the diagram we had for the PA negative. For this case, we had diagram in this way because we had loading joint at P. We had loading joint at A. Because of that, we said that when the load was at point A, we had reaction 0. We had 0 reaction. We had zero reaction. But in the previous case, let's think that think about that there was some triangle, there was some triangle, there was some one more triangle here. When you apply load here 1, when you apply load here 1, uh, there was some reaction here also. But I would say when you cut the section, it was giving reaction of 0.5. That means its component along the vertical was giving reaction of 0.5. Accordingly, this was some value of 0.5 times that d by h, 0.5 d by h, some sort of that. If this was some value, it was half of that. Okay. Let's take the third case. Third case of trusses, that is a n-type girder. N girder. Let's say this is n girder. Let's say this is n girder. N girder. How many members we have? Panels 1, 2, 3, 4, 5, 6. 6 panels we have. 1, 2, 3, 4. Let's say this is A, this is B, and this is yeah. We can write it as L1, L2. L1, L2 lower chord members. We have these lower chord members, and we have upper chord members U1, U2, U3, U4, U5, U6, U7, and we have diagonal members also, so that it forms the shape of N up to the midspan. Then after that, reversed in the reverse direction. So this is your truss and girder truss and girder truss, and we need to get the ILD for different members. Let's take the first one, that's U1, U2. First one is that U1, U2. Upper chord member U1, U2. Upper chord member U1, U2. So this is U1, U2. I would say this is the top member, and top member is having ILD of negative. Okay, top member negative ILD. After that, I would say the triangle. I would say what is the triangle we have? I would say the triangle is this is our triangle. This is our triangle. This is our triangle. Now loading, we don't care about the loading. See the difference between the previous problem, previous case, that was the diagonal members. All those diagonal members were inclined. All those diagonal members were inclined. But in this case, we have one is diagonal, one of the member is inclined, one of the member is vertical. One of the member is inclined, one of the member is vertical. In this fashion we have. So this is the difference between the previous problem and this one. This is your N girder. It takes the shape of N. It takes the shape of N. In the previous one, it was taking inclined N. This was inclined. This one was inclined N. For that, you had to see what was the loading joint, because if you take a particular triangle, we can have either these two critical points, or we can have these two critical points. But for the triangle, let's have that triangle, this one in this fashion and this one in this fashion. If we take any 2 points, is this the variation? I would say yeah, one of the joint is having the same one of the joint is here on the same level. So one of the joint is having the same level. Let's get the results. Let's get the results. Okay, so U1, U2. Let's take the U1, U2. U1, U2. I would say this is our U1, U2, and I would say the peak would be developed here. I would say peak would be developed at the opposite side. Peak develops at opposite side for the bottom chord. But for the bottom and top, peak develops at opposite joint. If it is mentioned that if it is mentioned the load is passing here and here, then I would see where can be the peak. But if it's not mentioning that where the loading is, this is the general that peak develops at opposite peak. Peak develops at opposite joint. If the member is this one, it's having 2 joints, and third joint is somewhere here, so peak develops at this joint, third joint. So that means peak develops here, peak develops here. So peak develops here. Let's say that peak develops here, and whether it's positive or negative, we said that top members having tensile, and that negative ILD. So peak develops here. That's value of some A, some B. So AB by LH, that negative diagram for the member U1, U2. AB by LH, negative. Now your A value is equals to 5. Your A value is A. Your A value is A. B value is 5A, and L is 6A, and H is H. A, 5A, 6A, H. Okay. Let's take the second one. Let's take the second one. Your member of U1, U2, U3, U2, U3, U2, U3. So second case is that U2, U3, this one. Let's take the triangle U2, U3, U2, U3. I would say this is the member U2, U3, and it's having triangle of, but the triangle is different. So U2, U3 is having triangle, this one. U2, U3 is having triangle, U2, U3 is having triangle of U2, U3 and L2. So this is the triangle. I would say peak would get developed. Peak would be developing at the L2. Would that be true? Is this the variation of the triangle? I think it's not. I think it's not the correct variation. I think it's not the correct variation here. Let's see why. Because up to the midspan it should have n type. It should be n type. So it should be in this way. It should be in this way. Let's show that. Let's show that. It should be n type. It should be in this fashion. After that, it should be reverse of that. Reverse n. After that, we should have reverse n. So this is not the, this was not the correct diagram. Now, the actual diagram would be in this fashion. So let's take the second triangle. Let's take the second triangle. Let's take the second triangle. I would say, let's have that. I would say this is your U2, U3, U2, U3, and you check the triangle it's having. I would say this is the triangle we have. We have this triangle. That means peak would get developed at the opposite joint. Peak develops at the opposite joint. Peak develops at the opposite joint. Let's have that joint U2, U3. That means joint peak develops at the opposite joint. That's the location here is this one, and we have only one critical location. That means you join them by a straight line. So this is your that ILD. And this value is equals to, this is 2A, and from the other side we have 4A divided by 6A, and we have that factor of H, AB by LH, AB by LH. This is the ILD for U2, U3. Let's take the third one, that's U3, U4. Third case, that's U3, U4, U3, U4, U3, U4. Let's take the third one, that's U3, U4. And its triangle is this one, U2, U3, U3, U4, U3, U4. Its opposite joint is here. Its opposite joint is here. Its opposite joint is here. Out of this U3 and out of this U3 and U4, its opposite joint in the triangle, that's at L4. So the peak develops at L4. Peak develops at L4. So the peak develops at L4. That means the diagram would be same negative diagram, and with the ordinates of that. This one is your A. This one is your B. But it's at the midspan. We say this is your 3A, and B is also 3 divided by 6A into H. AB by LH. This is negative diagram. ILD peak ordinate of 3A by 6A H. Now let's take the bottom chord members now. Let's take the bottom chord members now. Bottom chord members. Let's go one by one. Let's take the bottom chord members. Bottom chord members. Let's take L1, L2. L1, L2. L1, L2. Let's say that this is L1, L2. This is L1, L2. L1, L2. Now I would say, if this is L1, L2, what is the opposite peak? What is the opposite joint we have? I would say this is the opposite joint. That means peak develops at this point itself. That means peak develops at this location. Now we want to say, if this is the critical location, what is the peak we can have here? That means peak, only one peak gets developed. Now, if only one peak gets developed, how can you join that if only one peak gets developed? And that's also at the point where there is what you can call as, let's say peak develops here, and we have to connect it with the zero line. We have to connect it with the reference line from the starting. If the peak itself develops here, if the peak develops here itself, then how can you have that? That means there should be some line of 0. How can you join that? If let's say the point was here, this was critical location. I would say you connect this line, you connect this point to the reference line of point B and A in this fashion. Now if the point A is the critical itself, that means it's on the line itself, so you have to connect to that point to the same line. That means by a straight line. Let's have that analysis one more time. Let's take this section. Let's take the section. let's take this section, and we want to study that what should be the force in that L1 L2. What should be the force in the L1 L2 when the loading was either from the deck type or if it was through the through type. It does not matter here. Let's see why. Let's see why. Let's say load was at L1. Let's say load was at U1. Unit load of 1 was at U1, and you cut the section. You cut the section in this way. When you cut the section in this way, okay. When you cut the section in this way, then I would show this section in this fashion. This was your section. Then I would say there would be some force here also, and there is some force of L1 L2 here also, and there is some reaction of that reaction would be equals to 1. That reaction would be equals to 1. Would that be equals to 1 when load was directly above point A? Once it was a reaction of 1 upwards, that I would say summation of fx equals to 0. That means L1 L2 is 0. Okay, this is the first point. Even we got the 0 for the first case, even we got the 0 for the critical point. Once we got the 0 for the critical point itself, that means you have a 0 line, entire 0 line. And for all other values you can check also. If you take load at U2, if you take load at U2, I would say reaction at A would be, let's say 5/6. Let's say 5/6 would be reaction. And you still would be applying that summation fx equals to 0. This would be equals to 0. So this is having some 0 force. This is a 0 force member. We know that. Do you know that when we have two forces acting and there is one more, that third member, I would say the force in this one would be 0 for the trusses. Do you know that rule? So this same sort of that, I would say L1 L2 would be 0 for the entire thing. Once even we got one critical location. Where was that? I said you take that L1 L2, then you see the opposite joint in the triangle. I said that opposite joint in the triangle is at U1. Now I said that whether I have some peak here, I have a peak here at U1 or not. That was the thing here. And for that I showed that section also. I cut the section. I said force is 0 for also that when load was at that location A. And if the load 0 was that value, if the value was 0, that means entire all other values would be also 0. So this is your ILD for the member L1 L2. So let's take the second one, that L2 L3. Let's take the L2 L3 now. L2 L3. Let's take L2 L3. This is L2 L3, and we need to see opposite that joint in the triangle. Opposite joint in the triangle. What is the opposite joint in the triangle? Is that U2? Is that U2? So peak develops at U2. So this is the location that peak develops at U2. So there is some peak, and this is positive diagram. Why? For the bottom, we say bottom are having a positive ILD. Bottom having positive ILD. So let's have that positive ILD. And only one critical point is that's at the location of U2. Then you join them by a straight line. So this is your ILD, and value is AB by LH, where your A value is A, B value is 5A divided by 6AH. Okay, this is positive ILD for U2, U3. Let's take the third case. That's L3, L4. So I would say let's go for the L3, L4. Okay, L3, L4. You take the triangle. If this is L3, L4, what is the triangle we are having for the L3, L4? This triangle. So the peak develops at this location. So this is the opposite peak, opposite joint, the third joint we have in the triangle. So third joint is at the location of U3. So at the U3 location, our critical point would be there. So this is the location, that U3. And the diagram is positive. Bottom chord members, positive diagram. So this is your positive. And the value here is 2A, 4A, 6AH. AB by LH. Let's have one more. Let's take one more. That's diagonal members. Let's take diagonal members. Let's go for member. What you can call as. Let's take the member. What we call, what we say that member. U1 L1. I think we should take U2 L2 first. we are going to take U1, L1 later. U2, L2. Let's take U2, L2. Where is U2, L2? Can you guess? I think L2, U2, L2 is this one. Is this the U2, L2? I think this is the L2, U2, L2. Yeah, U2, L2. Let's think of that U2, L2. Let's say this is U2, this is L2, and I'm going to say what are the triangles where it's associated with? How many triangles we have associated with that U2, L2? I would say one of the triangles is U2, L2, L3, and one of the triangles is U1, U2, L2. So we have two triangles. Now I would say that we have two different peaks developed. I would say we have two different peaks developed, U2, L2. So for this case, let's first study, because they are vertical. Let's first study what you call as diagonal members. Let's not study first vertical members. Let's go for diagonal members first. 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 Your diagonal member is first one is that what you can call U1, L2, U2, L3. Let's take U2, L3. Diagonal member U2, L3. This one U2, L3. Now you take U2, L3 out, and I have these two triangles associated with that. These two triangles associated with that U2, L3. This was your U2, L3. U2, L3. I would say what are the opposite sides of that? Opposite sides we are having out of that. If this was U2, U3, U2, L3, what are the opposite joints we have? I would say one of the joint is here and one of the joint is here. That means two different critical locations are at level of L2 and U3. L2, U3. So one of the critical location is here, and one of the critical location is here. Because they are on the same line, U3, L3 is on the same line, so it does not have have any difference for that. So let's take that now. Let's take that now. That means if the member is diagonal member, do you know what's the variation? Is this the variation? Some sort of variation. We already saw that for the diagonal members, your ILD is some sort of that some ILD for shear force at any section. Some sort of that diagram. Whether it can be positive or negative, it depends on the direction of that arrow. We already saw that also. So if you talk about U2, L3, what is the orientation of that U2, L3? We got the critical locations. Once we got the critical locations, that what are the two critical locations? One is your L2 and one is your U3. Now we need to get the orientation of that. We need to get the orientation. Can you tell me the orientation of U2, L3? What is the orientation of U2, L3? Is it in this way, U2, L3? Yeah, I think it's in this direction, U2, L3. So I have to join that by a straight line in this way. That means the first ordinate would be in this fashion, same fashion. Then second ordinate would be from the top side. From the top side. U2, L3, positive. So this is the diagram we have. This is the diagram. Finally join them by a straight line. I would say this value would be equals to x. What is this value of x? Can you tell me what is this value of x? I would say this is a, and x d by l. X d by l, value of l is 6 times a, and this h. So 1 by 6th of d by h. And from the other side, I would say this ordinate is also x d by lh. This is also x d by lh. And value of x is equals to 5a. Is that 5a or 4a? I think 4a. 4a d by h, and l is 6a. 4a, 6a, d by h. So this is your ILD for your member U2, L3. Member U2, L3. Now one more thing is that you take the member, what you can call as U3, L4. U3, L4. So you need to get the U3, L4. U3, L4. I would say get the U3, L4. How is the orientation? I would say U3, L4 is in this way. That means then finally I would say, what are the triangles associated with that U3L4? I would say one of the triangles is in this way, and one of the triangles is in this way. Then I would say, what are the opposite joints of the triangle? Opposite joints in those triangles. I would say these two. These two are your critical locations. If this was U3L4, that means this location is L3 and this one is U4. So these two are the critical locations. One is your location of L3, one is your location of U4. So then finally, these two ordinates would be there. Then I would say the direction would be in the same fashion, that then you have that direction in this way. XD by L, your X, here the value of X is 2 times 2A by 6A D by H. For this one, 1, 2, 3, 3A by 6A D by H, X by L into D by H. This is your ILD for U3L4. ILD for U3L4. Do you have any other thing? We have that U3L3, U4L4. Can talk about U4L4. Can talk about U4L4. Let's talk about U4L4. Let's talk about U4L4. 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 Where is the U4L4 we have? Where is the U4L4? I would say U4L4 is this one. And if I take that and I have the triangles associated with that, I would say this is our U4L4. Now we have two different options here. Whether we have to see whether the loading is deck type or whether the loading is through type. Whether the loading is deck type or whether the loading is through type. If the loading is from the top side, let's say that let's finalize that loading is through type now. Let's finalize that loading is through type. For the verticals, we have to see whether the loading is through type or that deck type. Let's finalize that loading is through type. If the loading was actually deck type, then there would have been reaction in this one when loading was at this joint. We have seen that for the member CSE initially, the diagram was some sort of triangle, and after that 0. And for this case, we don't say that loading is from the deck type. We say loading is through type. If the loading is through type, let's write loading is through type. Let's say what is the ILD for that. I would say you take the triangle, then load. What is the critical location of the load? I would say the load location is this one. This is the load location, critical location. This is the critical load location for the vertical member. So this is different from these diagonal members. So vertical members are different from diagonal members. This is different. For the vertical members, we have different approach. So vertical member, you see the joint where the loading is possible. So U4L4, I would say that means only one peak is possible. That's at the location of L4. Now we need to get the value of that ordinate. We need to get that ordinate L4 for the verticals. Can you tell me what is the ordinate for the verticals? How can you get the ordinate? I would say if you cut that section, I want to see for this loading that when the loading was in this way such that let's have that. Let's analyze that. Let's say this was some truss, and finally I cut the section in this way. If I cut the section in this way, what I am left with, this T I have removed. Then finally I am left with some part I am left with, and there is some vertical also downwards, and we have that in this fashion. So I am left with this part only. There is some also sides also there here. We don't care about it. We got this truss finally this section. Now if I apply that load on this joint here, 1, and that means reaction here would be 0.5 by the symmetry. And I would say what is the force in this member? That's your U4L4. So U4L4 force would be 0 because all the loads is transferred to this point. Now similarly, if the load was transferring to this point, see, if the load is transferring at the L4 location, that's through at the that is the loading is through type. If the loading is through type, that means at U4 there is no load. Directly you can say if there is no load at the U4L4, that means there is no force in this member also. But if the loading was deck type, if the loading was deck type, if the loading was deck type, and we cut the section that this was your point S, and there was some section here, and if the loading was here, load was at joint S, that's at the deck type. Let's say this S was here U4. If the load was applied at U4, there would have been some reaction negative, that's compressive, towards the joint F, that was also equals to 1. So the diagram would have been -1. But for this case, I would say on this section U4, I am not applying any external load, so this member would be, this force would be also 0. So ILD would be equals to 0. 0 diagram, ILD. And for all other cases, you can have ILD equals to 0. We have performed analysis of that also in the previous lecture. Now we are left with those verticals. We are left with verticals. We are left with verticals. Now we are left with verticals. We are left with verticals. One is your L2, L3, L1, L2. Let's take the first case, that's L1, L2. L1, L2. L1, L2. Let's have that L1, L2. So this is your L1, L2. Where is your L1, L2? So this is not L1, L2. Yeah, we have performed analysis of that. We have to take the U1, L1, not that one. U1, L1, that's this one. Vertical members we have to take. U1, L1. U1, L1. U1, L1. So I would say that you have this member U1, L1, U1, L1. Then you take that triangle, you take that triangle, you take that triangle, U1, L1, U1, L1. Now, I would say the loading is through type. I would say the loading is through type. Now, if the loading is through type, that means your joints are subjected to loading are L1 and L2. So your P coordinates gets developed at L1 and L2. P coordinates gets developed at L1 and L2. So the difference in these previous problems that we have diagonal members, in that we have different approach, and in this one inclined members we use different approach. You say that where is the loading applied? I would say loading is applied at L1 and L2. That means two P coordinates would get developed. One is your L1 and L2. So I would say two P coordinates gets developed. Two P coordinates gets developed. Let's take those two P coordinates. I would say there is one P coordinate here, and one P coordinate is at the location of L2. Now we need to say whether they are positive or negative, and what's their value. Let's analyze the case one when the load was that at the location of L1. That means if the load was at joint. Now if I cut the section, I would say if I try to cut the section, I want the force in the member U1, L1. So I would cut the section in this way. So there is some reaction here. There is some reaction here, and this is my force, unknown force F, in the member L1, U1, L1, vertical member. There is some horizontal. I don't care about that. I have to apply that summation Fy equals to 0. Now the thing is that load is applied at the joint L1. If the load is applied here, unit of 1, and I would say reaction is also, the support is giving also reaction of 1. I would say 1 plus minus 1 plus F U1 L1 equals to 0. That means F equals to 0. So force at this critical location is 0. Now I had to take that second condition when the load is at what you call as L2. When the load is at L2. Let's have the second case that load is at L2. Load is at L2. So there would be some reaction. Can you tell me the reaction when load at L2? If the load is placed at L2, can you tell me what is the reaction we can have? That's 5/6, because total span we have 6 segments. We have total 6 segments. Think of a beam that's loading subjected to at a location of A and 5A. I would say reaction here is 5A by 6A into that unit of 1. So 5/6. So reaction is 5/6. So I would say summation Fy equals to 0. So 5/6 equals to minus times F that force. So I would say that force is minus 5/6. Can you say that force is minus 5/6? So negative value, and I know that critical location is at that location, so minus 5/6. So there is some value of minus 5/6. Then once we got the two critical points, what you have to do? You have to join them by a straight line to the ends. So here Had here been any value, it would have been equals to 1. That is 6 by 6. And this value we can also write it in terms of that a by l and b by l. This value is equals to b by l, and this value is x by l, because your x value here is 0, so that's why this ordinate is 0, x by l, and this value is b by l in this direction. We can also write it, this is x by l, but the direction is in this direction. So this is your x b by l, and this is negative. For this first ordinate, we say this value of x is 0. So this is x by l, and this one is second one is b by l. It is some sort of that shear for ILD for any shear force at any section C. We have this ordinate, we have this what you call as ILD. But based on that, we say that we got that here at the critical location of 1, we had 0 ordinate. That means only one ordinate, only one peak we had developed. So then finally we can say there is some triangle form. There is a form of triangle variation. But it's not that of AB by LH. It's not that of AB by LH. It has developed because of this condition that force is 0 when load was at joint A. When load was here, we got force 0. Otherwise, would have been some value here also. There would have been some value here also. This is not AB by LH. Okay. This was vertical member. Let's take the second vertical member. That's U2L2. U2L2. Let's talk about U2L2. 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 Okay. U2L2. Which of these is U2L2? U2L2. Which of these is U2L2? Can you tell me which of these is U2L2? U2L2. I think this one is the U2L2. This one is the U2L2. Let's take that outside. If this is U2L2, if this is U2L2, and I have to make the triangles also. I would say one of the triangle is in this direction, and one of the triangle we have, that's this triangle. So we got the two triangles. Then I would say for the through type loading, can you tell me the joints we have? Can you tell me the joints we have? For the through type loading, what are the joints that are applied loads, that have been subjected to loads? I would say one of the joint is this one, and one more joint is this one. So that means two critical locations. One is at L2 and one location is at L3. L2, L3 is the critical location. So L2, L3, these are the two critical locations we have. That means we need to get the values of that ILD at those two critical points. Now we say that how can you get the values? Now its value. If you want to do an analysis, you can get the values. That's for sure. But I would say directly, how can you get the overall value? So when there was inclined member, I say that the variation. I said there is some value. We have one of the ordinate is above the line and one of the ordinate is below the line. Such that final value here is some value of xd by L into h. Divide me. And here, similarly, here is also some value of xd by L h. X is in this direction, here x is in this direction. And this was case of diagonal member. But if you talk about vertical member, I would say your factor of that d by h is not there, because this d by h has came into effect because of member was diagonal. Because your member was diagonal, this effect has came because of that. D by h has came because of the fact that member was diagonal. It was having some height of h, it was having some diagonal of h. So this was some sine theta component. Do you know that? This was because of that sine theta component. We are trying to resolve that force along the y direction, and the vertical diagonal member is having some component f sine theta, and because of that we have some h by d, hypotenuse, height by perpendicular by hypotenuse. From that we got some d by h cosecant theta. Cosecant theta equals to d by h. But if the member is itself vertical, that means you don't have to get this factor of d by h. You don't have to multiply this factor of d by h. That means the ordinates would be developed. Let's say the ordinates developed are same in the same fashion. Let's say the ordinates for the vertical are also developed in the same fashion, but the ordinate values would be equals to x by L only. This value is equals to x by L only. Hope you get it. This is for the vertical members. Remember that. You can see that in the previous problem we said when we took u1 l1, when we took u1 l1, u1 l1, when we took u1 l1, what was the ordinate we got? Do we got the diagram in this fashion? Do we got the diagram in this fashion? We had two critical points. One was here, one was here, and I said this is equals to 5 by 6. For the second ordinate, we have direction in this fashion. That's b by l. That's 5a by 6a. And for the first case, we said x equals to 0. 0 by 6a. So 0. But that means we don't have to multiply that factor of d by h here. D by h is not there. Similarly, in this case, there is no d by h. D by h is not there. It's only for the diagonal members because of that component sine theta component, vertical member component. Okay. Hope you can get it. Hope you enjoyed it and you got it. Let's get the values now for the what you could call as next member, vertical member. That's u to l2. u to l2. I would say this was your that we got that. I think you for the u2 we got that. I think we have performed that analysis. Let's say this was u to l2. u to l2. I would say loading joints are at l3 and l2. So these are your loading joint. That critical locations are these two. These are our critical locations. Now the thing is that whether the starting would be upwards or it would be downwards. So for that I have to take, I would say, if you got the direction of starting direction for the diagonal members, then after that for these this is the inverse. For these we have this inverse of that. We have the inverse of that. We have the inverse of that. We have the inverse of that. So if I take any diagonal member, let's take that u3l3. Let's take u3l3. u3l3. If I say u3l3, what is the orientation of u3l3? Is that in this direction? If the u3l3 is starting in this direction negative, that means u1l1 would be in the opposite direction. u1l1 is in the opposite direction. So u1l1 would be starting in this direction. So second ordinate would be below the line. So starting for the u1l1, u2l3 it would be positive, and after that it would be negative for the two coordinates. So this part is not there. So this is your variation, and this value is equals to x by l, and this value is some value of x by l also. This value is equals to a by 6a, and this value is equals to 4a by 6a, this ordinate. And if you extend it, you would get a value of that's unit of 1 for l by l. See, when we performed that variant truss, when we are looking for that variant truss, I said if I take this element, if I take this member, I would say what is the ILD of this one? I would say you orient it in this way. So starting, if the start is in this way, that means the other side would be below the line. So you draw this ILD for this one. And but if I talk about this member, if I talk about this member, what is the ILD starting ILD looks like? I would say you orient it in this way, starting in the same direction you had to orient it in this way, that way. That means opposite side above the line. So this was your diagram. Similarly, to get the ILD starting for the u2l2, that's vertical member, how can you get starting part, whether this is above the line or below the line? For that you have to take that member before that or just after that. That's diagonal member. So if I take that diagonal member, that u2l3, that was in this direction, that means for the u2l3 it was starting negative. So for the vertical it would be starting positive. So for the u2l2 it would be starting positive, and after that in this way. Hope you are getting that. Hope you got it. Now let's take that third vertical member that we call as third vertical member, that's u3l3. Let's take the u3l3. Now where is the u3l3? Is this the u3l3? Now let's separate it. Let's take it out, U3L3. This is U3L3. And can you tell me the triangles we have related to U3L3? One of the triangle is this one, and one more triangle is this one. So then we say the loading is through type. The joints associated with that loading, that is L3, L4. So critical location for the that ILD are at L3, L4. So one of the location is L3, one of the location is L4. Now I would say, what is the diagram for this one? Can you tell me the diagram starting? So I would say the starting diagram would that be in this direction, or would that be in this direction? I would say if you analyze that what you call as diagonal members, they are in this fashion. That's they are starting in negative fashion. That means for the vertical they would be starting in the positive side. They are starting in the positive side. So they are starting in the positive side. That means from the other side they are having negative value. So this is negative, this is positive, and then join them by a straight line. So this ordinate would be equals to x by L and total of 2a by 6a, and this value is equals to 3a by 6a. That's also x by L. So this is your ILD for member U3L3. Yeah, this is the end of the what you can call as end of these things. So the difference we got that comparing, if you compare vertical with the diagonal members, we say the difference here is that here the ordinate, the diagram is same. Let's say the diagram is same, but the thing is that diagram is same, but the ordinates are differing by a factor of cosecant theta, by that factor of cosecant theta. So if this was some value of x by L d by h, it was also some value of x by L d by h, but here we have only value of x by L, and we have only value of x by L, for the value of x is in this direction. So we are applying this factor of cosecant theta here because of this. When you resolve that force along the vertical, this was your force along the diagonal, then we say what is the component of that, f sine theta. Then finally we write it f equals to some value divided by sine theta, that's value into cosecant theta, that's value into d by h. That's your x by L d by h, x by L d by h, same value of x by L and d by h, x by L d by h. Okay. Let's go for few more problems. Let's go for few more problems. We're going to see whether we have completed the same part again. This is 5 by 6a. That's okay. QC. Now we would say, if your member is PA, let's analyze that member PA one more time. That's U1L1. Let's analyze the member U1L1 again. Let's analyze the member U1L1 again. If you try to analyze the member U1L1 one more time. So we have got the ILD for the U1L1 when the loading was through type. So this was your U1L1, and we said that it's having this triangle, and for the through type we have two loading joints critical. Then we said the diagram would be in this way. This was your 5 by 6 negative. So this was your 5 by 6 value here at this location, 5 by 6 ILD in this way. This was your 5 by 6 negative. Now second case is that if the member is, if the PA is having deck type loading. If you talk about the PA, it's having deck type loading. Let's take that same member again, but the loading is deck type. If the loading is deck type for the member U1L1, can you tell me which of the joint is having the loading? Is that U1 only? That means U1 only is the critical point. If the loading was deck type loading, so load is applied at the U1, so that is critical location is only 1. So if you have that ILD, I would say your critical location is also only 1. Now to get the force, I would say, how can you get the force for this member? That means you have to cut the section in the same way you already have. So this was the section you already have in the previous problem also. Once you cut the section, there is some reaction upwards, some reaction of RA, and you are cutting the section. There is some force in the member. Let's say this is force F in the member U1L1, and there is some horizontal force also. I don't care about that. If I apply that, summation Fy equals to 0, but I'm not applying the load at this junction, and I'm not applying the load on this point. I'm not applying the loading at this point. I'm not applying the load on this point. I'm applying the load from the top side. I'm applying the load at the point U1, and I'm applying the load at the location of U1. At this point, I'm applying the load here. But my section is not having that load. If I got the section here, it does not have the effect of that load. It only cares about the value of reaction. So if the load was initially if the load was just above that point, if the load was here, I would say reaction would be 1. If the reaction was starting equals to 1, that means same reaction would be negative times here the force would be compressive, that's towards the joint, -1. So starting diagram for this one would be negative -1. So I would say force in the member, what you can call as U1 L1, that is minus times reaction A. That's minus times reaction A. And for all values now, if I place the load at all different locations, let me place the load here at joint U6. If I place the load here, I only care about that section that's having some reaction here, some reaction A, and we have some force here F. I would say, what is the reaction we have based on that? I would say some reaction of 1/6. I would say some reaction of 1/6 would be there at the support A. That same value would be negative times the value of force in the member U1 L1. So that means here the value would be 1/6. So here the value would be 2/6. Here 3/6, 4/6, 5/6, and 6/6, such that its value equals to 1. So then I join that by a straight line. That's the negative of reaction A. That's the negative of reaction A. So this is the ILD for that's the ILD for member U1 L1, vertical member U1 L1, but at the rate of deck loading. And it's similar to that of a reaction by the support. If you talk about what is the reaction, what is the ILD for the reaction at A, I would say the reaction at A, we know that for a simply support beam, this is the variation +1, and for this one it's negative of that, because we have to maintain the equilibrium, vertical force equilibrium. So this is your variation for that. Now if you talk about SE deck type and SE through type, SE deck type and SE through type. So we already got that U4L4. We talked about earlier U4L4. Yeah, we talked about that. So for the through type loading, U4L4 diagram was 0, and this was for the through type. Now if there was deck type loading, that means load was applied from the top at the joint of U4. And if I got the section, I would say here there is some force of F, such that force in the member U4L4, that was minus times that 1, minus times 1. Then finally for all other values it was 0. So diagram would have been in this way: -1, -1, -1. So this was your diagram, ILD for that in this way. We have already performed analysis also in the previous lecture, and this is the shortcut that what is the nature of that. So everything is over. We got it. Okay. Now the second topic is that we have one more girder, that's N girder, but the diagonals are reversed. N diagonals, this is also N girder, but the diagonals are reversed. So we can say this is N reverse. So let's write that it's N diagonal. It's also N girder. But diagonals are reversed. So different from the previous one. And diagonal reversed. Diagonals reversed. We have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. 1, 2, 3. Let's say this is the bigger one. 1, 2, 3, 4, 5, 6. Then we have this support also. Support A, support B. And we have A, B, C, D, P, Q, R. P, Q, R, S, A, B, C, D, A, B, C, D, E. Now we have diagonal members also. In the previous one we had this one N, and for the wire and truss, when we did the analysis, we say the wire and truss was in this fashion, that the starting the starting of this lecture, it was in this fashion. And we made those short tricks. We made all those short tricks. Now finally that we made all those short tricks up to this point. Up to this point, we made all those short tricks that were valid for that are valid for n and that inclined at n. So that was inclined n. That's variant truss. Variant truss is in this way that we have this truss in this fashion. So this is n but inclined n. But this one was your vertical n. And all those shortcuts up to this point, they were valid for n. Now for this one, now for the reverse, and we have to reverse the direction. That's the difference. We have to reverse the direction. Let's see where we have to reverse the direction. We are going to see that. So if the diagonals are not in this n direction, they are opposite of that. They are opposite of that. That's to make the difference. Let's have that highlight. Let's highlight that. Let's try to highlight that. Let's try to highlight that. I would say in this direction. You have to go in this direction up to the midpoint. Then after that, you have the actual n. You have the actual n after that. So that's the what you call as the diagonals are reversed. Let's study now. I would say what is the force. Let's go for the member PQ. Member PQ. Top member PQ. Top member PQ. Top member PQ. We would see whether there is any change in the those shortcut tricks. Whether there is any change. Let's go for the PQ first. I would say PQ. What is the PQ we have? PQ is the top chord member. Top chord member PQ. And what is the triangle it's having? So it's having a triangle of PAQ. So PAQ. Then I'm going to say. And question is saying that if you calculate for the top chords for the top chord members, it's mentioned that when you're solving for any member ILD, if you're solving for ILD for any member, this is mentioning from the question that for a calculation of ILD for any member, if the member was top chord member, you take loading as deck type. You take loading as deck type, and if you are calculating for bottom chord, you take loading as through type. You take loading as through type. So for the first case, if the member is PQ, that's top chord member, we have to take loading as deck type. If the loading we have to take as deck type, that means we need to see what are the two critical joints we have. I would say one of the joint is here and one of the critical location is here. So we have two different P coordinates. We need to get the two different P coordinates. Now we are going to see what are the values we have at these two critical locations. Other way is that directly you can say if the loading is, if this is your joint, if this is your PQ, then opposite to that there is some one more joint, that's A, and on that A there is some peak developed. So only one peak you have to calculate based on that previous trick. But if I go with the problem, that top chord, that we have to just now calculate what are the values at those two critical locations. Now one thing is that this top chord members, they are having the diagram in this fashion. That some sort of ILD for any bending moment at any section. ILD AB by LH. This is the variation. Now we need to see that. What is the actual variation? Let's go for that. Let's apply the load at joint P. And I want, which are the forces I want? I have to get the force in the PQ. Now without any concept of ILD, if you just cut the section at PQ, can you tell me what is the force in the member PQ? If you cut the section in this way, let's assume that there are general loadings we have general vertical loadings. Can you tell me what is the force in the member PQ we have? Based on the method of sections you might have studied, based on those rules for solving the truss forces. Can you tell me if this is your PQ, you cut the section at this joint, there is no load. Even if there is vertical load of V1, that gets transferred along this line PA, I would say horizontal force would be 0 here. So I would say PQ line would be 0 line. PQ ILD would be 0 for all values of loading. At every joint you place loading, whether on the top or on the bottom, I would say here the value of that what you could call as value would be 0. Value would be 0. Value equals to 0. Value is equals to 0. So if I say that let's assume that there is some force. Let's assume that there is some force, but there is no horizontal force acting at that joint. Let's assume that there is some force F also here, horizontal force, and at the joint it should be joint should be in equilibrium. There is no one to balance this horizontal reaction. So I would say this has to be 0. There is no any other option. So that's ILD for this one. First case, that PQ, that's 0. Now second case is that RC, diagonal RC. Let's talk about RC. So RC is this one. This is your RC. Okay, let's separate it out. Let's take it out. This is RC. This is RC. Let's have the triangles we have related to RC. What are the triangles we have? Okay, so we got this one. And I would say, what are the two opposite sides of the triangle? What are the two opposite points of this what you can call as RC? Out of this triangle, out of these two triangles, we have to get the opposite ordinates of this RC. Out of this RC ordinates, we have to get opposite these joints. I would say these two joints would be critical locations. These two joints would be critical locations. One is at the level of C, and one is at the level of R. So one of the location is here, one of the location is here. So let's take that. I would say your one of the critical location is at the level of Q, but because the level of Q is along the line of C, so they are on the same line. And similarly, your level of D, it's also in the level of R. So we got the two critical points for the diagonal member. Now, our previous assumption, our previous short trick says that if your member is a diagonal member, then you place that same member, then you orient that same member at the starting point, such that in that same fashion you would have starting ILD. So for this case, if your member was RC in this way, so your starting would have been in this way. That was a trick for the N case, N type girder, or that wire and truss having that N. But because your diagonals are reversed, so it's that means your diagonals diagram would get changed. The diagram for your diagonal members gets changed. That's a direct representation, because it's directly saying from the topic itself, it's saying that diagonals got reversed. That means the diagram gets reversed. If the diagram initially was if the diagram for the RC initially would have been in this way, that's upwards, starting upwards. So this was initially, we can say this was for the N case, but for the reverse N, your diagram would be downwards, starting in the downward direction. So that means it starts in the downward direction, then from the other side it's upwards. So finally this is negative, positive, then you join the two. So I would say this value is equals to, let's say the panel length is A, I would say this value is A by L and D by H, this factor of D by H, because this is a diagonal member to have that sine component. So this is factor of cosecant theta, D by H. And this value is 4 times, this value is 4A by 6A D by H, or we can say X by L D by H, X D by LH, X D by LH. So this is your diagram for the member. This was for the member of RC, diagonal member ILD. Now one more thing is that you need to get the QC deck type. QC subjected to deck type loading. QC deck type. Let's talk about QC, that's deck type. QC deck type. So vertical member, QC deck type. QC deck type. So if the member is QC, this is your QC member. And now see the triangles we have associated with that QC. I would say this is one triangle, and one more triangle that is associated with QC, that's QAC. Now condition is that, see, what is the condition we can have? You can't directly say for the QC, you can't directly say what are it's a function of joint, it's a function of loading, on what joint you are applying the loading. If I talk about deck type loading, that means critical joints would be these two. Then if I talk about through type loading, the joints critical are these two. So this is the difference. So we have to see which of the loading, where the loading is applied. So let's say that this was your QAC, and this was your QRC, this was your QC, and I would say what's the loading. So question mentions that ILD for QC, ILD for QC, for the loading of deck type. So deck type loading, that means the critical location is the Q and R. So Q and R are the critical locations. That means same those as that of previous problem we had, Q and R, Q and R. And we know that how can you draw the ILD? Is it in this way or is it in this way? Do you know that? How can you draw? So for that I have to say what is the diagram for the diagonal member. If this was your diagonal member QC, it is starting would have been in this way for the end girder, but it was because it is reversed, so it starts in the opposite direction. So CD, I would say QC starts in the opposite direction in this way. QC diagram was in this way, QC diagram. And according to that, I would say the diagram for QC, sorry, this was not QC, this was diagonal. I was talking about diagonal RC. I was talking about diagonal RC. This was for the RC. We got the diagram for RC for the reversed case. You can see the previous solution we have. This is the diagram, and opposite of that would be diagram for the vertical member. Opposite of that, so opposite of that would be in this way. And finally, from the other side, you have to join this also in this fashion. So this is starting from positive, then after that negative. And this value, is it xd by lh or it's only x by l? Is it xd by l h or it's only x by l? What do you think? If you have vertical member, do you have to have the effect of that component, sine component? I don't think so. I think it should not be there. So this is the value, that x by l. And what is the value here? X value is a, l is 6a. And for this part I would have the value of x equals to 1 2 3 4 4a divided by total length of 6a. And if I try to join it up to the point, if I try to extend it, I would say this value is also a unit of 1. Total unit is 1, but I don't care about that. Okay, let's take the third one. That's RD through type. I think same diagram might get developed. RD through type. Where is RD? I would say RD is here. This is RD, and it's having through type. RD through type. So RD is this one. It's having two triangles. One is your RCD and RSD. RCD, RSD. Okay. So these parts we have to remove. This is RCD and this is also RSD. So finally, I would say because the loading is through type, that means the critical joints are at this location of C and D, at the location of C and D itself. So it's similar to the previous problem. Critical location is at C and D. For the case of when the loading is through type, let's go for that. I would say we have two peaks. Now we need to say what is the direction for the vertical. If this is the vertical member, how should we start for it? I would say you start firstly for the diagonal member. If the diagonal member is in this fashion, but because if your member is RC in this fashion, but it's because it's diagonal is reversed, so actual RC is that downwards. Actual RC is in the downward starting, so negative for the diagonal. That means for the vertical, it's opposite. That's a positive side, positive start. After that, finally in this fashion. So this is the variation, and this value is also equals to x by l, and this value equals to x by l, and that's 4a by 6a, and this one is a by 6a. We already have those in the previous problem also we did. Okay. Now the thing is that you need to get for PA deck type. So let's have that PA deck type. If I cut the section in this way, If I cut the section in this way, PA deck type, if I cut the section in this way, now because the loading is deck type, can you get the ILD directly? Can you say what is the diagram ILD directly? Can you get the direct ILD? I would say if this is the joint, I am applying the load on this joint. Can you tell me what should be the value of the force in this member? Should be the, upwards towards the joint. F should be equals to 1 also. That's minus times 1. Should that be minus times 1 when the load was just at that point P, because of deck type loading? I would say the force ordinate in the PA would be 1, minus times 1, minus times 1. And but if the load is at Q, can you tell me what is the force? Because then after that, I would say if this is your section, load is somewhere here, and on this joint there is no load. I would say this is also 0, this is also 0. So after that, on all points you have ILD of 0. On all points you have ILD of 0. So then I would say, how can you then finally join? How can you finally join it? If all points are 0 and you have ordinate here 1, then where can you join it? So where is the possibility you can join it? What is the possibility you can join it? I would say once you cut this section here, there's a possibility if the load was here, it would have some reaction. Because of that, there would be some reaction here, reaction A on the bottom side, and based on that, there would be some force also, might be some force here also, up to the point when it reaches to the point Q, So I would say the critical location would be in this, up to this point. Now one more way we can do, we say that if this is your PQ, and we need to get the force in the member PA, I would say there's a possibility that once we select the triangle, that critical locations are in the triangle itself. The critical locations are in the triangle itself. Once I said that unit here is 1, that means then after that we said F equals to 0 for all locations. Then how can you join that? Why do you have to join it to the reference line? I would say on the point Q itself. So diagram would be in this way. This is your P. This is your PA deck type. -1 deck type. And one more thing is that QC through type. Let's go for QC through type. Why is QC? Can you get why is QC? I would say QC is vertical. Let's have that triangle. Let's have the triangles with that associated with that QC associated triangles. I would say this is QC. The triangles associated with that are one is your QAC and one is your QRC. Then after that, for this triangle, because the loading is through type, can you get the ordinates? Can you get those joints? Because of the through type loading, I would say peak ordinates. Peak gets developed at A and C. So one of the ordinates gets peak here, one of the ordinates here. So join them by a straight line. Now we need to get the values. Do you know for the vertical what is the variation? That's some variation of x by L, and this is also some value of x by L. But because for the first point we have x equals to 0, so this value would be 0. And for the second case we have x equals to 5, so this should be 5a by 6a, and negative, I think negative should be there. I think this should be the variation. We have already solved one problem in the N girder also, so this should be the variation. So this should be x by L minus times, and this should be 0 because x equals to 0 for this case, and for this case we have x equals to 5a. Now one more problem is that you need to get SE through type. Let's have that SE. Why is SE? That's vertical member. SE is a vertical member. So SE is a vertical member. This is SE. Now you need to get the triangles. We have these two triangles, and loading is applied at those joints here. And then finally, if I apply the load just at the point E, that means the reaction developed would be here. That's a positive one. Because if you see the direction, this is downwards. It's tensile force developed in the member. That's towards the away from the joint, so positive tensile. So unit of 1. At this location we have unit of 1, and I would say for all other values it's 0. For all other values outside this Outside this is 0 0 0, this is 0 0 0. We have performed the analysis for this one in the previous lecture. So this is positive value of 1, and there's some linear variation between, similar to that of this triangle. If you take this triangle in the truss, we are having same ILD for this one. This is unit of 1. Let's assume this is unit of 1. Same diagram we have here. That you can show by also by performing analysis also. Now let's go for SE deck type. SE deck type. SE deck type. Now, if the load is not here, if the load is not applied from the bottom side, load is applied from the top side. Load is applied from the top side. If this was your SE, load is applied at this joint only. If the load is applied only at this joint, that means only one critical location. Only one critical location. And for that also, if I cut that section, if I cut this section, I would say from the bottom side, if I cut the section in from the bottom side, if I cut the section from the bottom side, I'm applying from the top some loading of 1. From the bottom side, there is no external load, so force in this one would be 0. So I would say the ILD would be a 0 line. This is for the SE deck type, and this one was SE through type. Okay, now we have one more problem of that. We have one more problem. We take one more. We're going to have one more sort of problem. That's we have truss 1 2 3 4 5 6. They are some sort of n type. So we need to get AC, QC, QA. Let's say this is A. We have this one QRS, and we have this one CDE. We need to get ILD for AC. Let's go for AC. Let's go for AC. If I have this AC, if I cut the section in this fashion, can you get the AC? What should be the value of AC? So I would say for the AC, and the loading is through type. Loading. Now I would say where is the AC? It's a bottom chord member. So diagram would be tensile, positive ILD. Would be, so if I have this triangle, this is ACD. So opposite to that means loading is at this joint, and loading is at this joint. Loading joints are A and C. So that means A and C are the peak points. But the diagram, because A is at the 0 point, so I would say 0 at the support level, at the starting point. So only one peak would be developed, that's at point C, and having ordinate of AB by LH. Now that means peak would be developed at C. That's because the member is bottom, and it's having the ILD in the form of that ILD for bending moment at any section. So this ordinate would be here AB by L divided by H, and that value of A equals to A, B equals to 5A, L equals to 6A, and H equals to H. So this is your value here, and this should be negative or positive. This should be positive ILD. And let's take the that member QC. Let's take the member QC. What is the member QC? QC is vertical member. If you talk about vertical member, it's having two triangles. This is the QC member, and we would say, what are the loading joints we have? One joint is this, one is this joint, and one is this joint. Now that means three critical joints. Now if I apply the load at this joint, at the joint C, I would say the force in the member QC would be 1. So that's positive 1. So a unit of 1 would be developed at this location. At the critical location of C, a unit of 1 has been developed. Diagram of 1 unit has been developed. And for all other values, you can say, and the force is linearly varying up to these 3 critical points. We have these 3 critical points, A, C, D. How can you have these 3 critical points? I would say they should be in such a way that they should be linearly varying up to this point. Then after that, there is a zero variation. You can check that also. Let's apply load somewhere here. If you apply load here, and you are calculating force in the member CD, let's try to make a section. Let's try to make a section. Let's cut the section in this fashion. Let's cut the section in this fashion. So you're applying load here. There is some reaction here. Okay, no problem. But what is there any external load on this section? I would say no external load is there. Then I would say directly, since there's no external load, this reaction would be 0. But maybe there might be reaction. Let's say there is some FB1, there is some FB2. There might be some forces FB1 equals to FB2. Like this one is in this direction and this one is in opposite direction. Maybe there might be some force. We don't care about the horizontal, but we are caring about the vertical, because there is no any other force and we have only one vertical member, so this should be 0. This should be 0 for all other loads. For all other loads, that if the load was anywhere here, anywhere here, anywhere here, we are talking about the through type. So this is the variation that it's having a maximum of 1 positive. This is for the member of QC. Let's take the third one. That's QA. Where is the QA? Where is the QA we have? I think this is the QA we have. So if we take this one, the triangle associated with that, what are the loading joints? So two critical loading joints, and QA is diagonal member. So for that diagram is some sort of in this fashion, but one of the joint is at the 0 line. That means for this one, this is x equals to 0. So this ordinate would be 0. We know that the equation is xd by LH, but if the value of x is 0, so this ordinate, we know the critical location is at this one, but x here is 0. So the ordinate here is also 0. And for the location of C, at the location of C, I would say ordinate here is x. Value of x equals to some 4e or 5e. This is 1, 2, 3, 4, 5, 6. 5a by 6a and d by h. So this is your value here. So finally join them by a straight line. Negative diagram. Is this the diagram? Yeah. xd by LH. Yeah, this is the diagram. Okay. Now the final case of this, we call it as hoe truss with inclined top chord members. We have bottom members 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We have 6 members. Okay. Then we might be having our bottom that main member at the mid part. Then after that we have the top members that they are linearly varying. They are arranged in this fashion. If we have 6 members, 1, 2, 3, 4, 5, 6, 1, 2, 3. That means one member is here, one member is here, one member is here. Then they are in the form of n. They are in the form of n up to the midpoint, up to the mid part. Then after that reverse n, reverse it, then you reverse it, then you reverse it. So finally this is your truss. This is your truss. We say this is hoe truss with that inclined top chord members. Now the thing is that we need to get, let's call that as A B C D E, and this PQRS, and then you need to get that loading is through type, and you need to get the ILD for, let's go for the first one, that's AC. Can you get the ILD for AC? Similar to the previous problem we have. Can you get the ILD for AC? If this is ILD for AC reference line, so if I cut the section here, this is joint A. If I cut the section in this way, this one, I would say there is no one to balance the horizontal one, so this one should be 0. If I say summation FH equals to 0, that is 0. So ILD is 0. Let's go for the second one. That's PQ. Let's go for the PQ. Where is PQ? So this is inclined top chord member. Let's assume for now that this is a top chord member. Let's say that PQ is a top chord member. Let's have the triangle associated with that. Let's assume that it's a horizontal member. Let's say this is a PQ horizontal member, and we say what's the triangle associated with that? I would say this is the triangle. And where is the loading applied? At the C location. That means the critical location is the point C. So the critical location is at the C, and I would say what is the peak ordinate at this location C? So I would say this value is A and B value is 5A, and total length is 6a divided by h. So AB by LH, AB by LH, and this is the top member is having negative, top member negative. But the thing is that your h is not, this h is not, you have to take the value of h that's perpendicular to, that's perpendicular to a direction of that. I would say if the member was from this point, I have to take the that vertical height h. If this was vertical and this was making 90 here, I would say this value is equals to h. But for this case, this is not this length. There might be some length of h here. Let's say this is h2. If this is h1, this is h2, this is h3, this is h4. I would say here the value should have been value of h2. But the thing is that it's not, we are not having a member that's vertical. It's a that's little bit of inclined. We are having some alpha at the bottom, at this side. We're having some alpha here. We're having some alpha. So I would say you have this member. You see the triangle associated with that. I would say the triangle associated with that is this one. And the theta here is not 90. And to make the 90 theta, I would say you draw a line. You draw a line from this one. So some sort of in this way. So if I draw the line, so I would say this is your 90, such that it's perpendicular to that. I can show from the other side also. I would say this is the 90. Here the angle is 90. I have to make sure that the angle is 90. So for that, I would say this length, this is your length of h perpendicular 1, h perpendicular 2. So this is what we have to write here. So we need to calculate that h perpendicular 2. If you are provided with that theta, you can, if you are provided with that alpha, you can get the value of that h perpendicular 2. And similarly for the, let's take the case that QR, member QR. Let's see where is the member QR. And member QR is a top chord member, so diagram would be negative. And we are having the diagram in the form of that ILD for bending moment at any section, AB by L and divided by H. So we have this one, then the variation is in this way. So this is your QR, and we have an ordinate here D, and loading is applied at the joint D. Loading applied at joint D, so critical location is D. So I would say bending moment diagram is that ILD is a negative diagram. ILD is a negative diagram with the ordinate of peak ordinate of AB by LH, where your A is equals to 2A, B equals to 4A, L equals to 6A, and H, we have to take the perpendicular H. We don't have to take the H3. We don't have to take the value of H3, but we have to take the perpendicular direction. We have to take the perpendicular. Let's say the perpendicular is some sort of this one. Let's say this is some perpendicular. Let's call it as H3 perpendicular. And this length was actually H3. We have to take the length perpendicular to the that QR, perpendicular to that member QR, H3 perpendicular. Now let's take this third one. This was also negative diagram. Let's take the member CD. Let's take the member CD. Why is the member CD? We have member CD. CD member is bottom chord member. What is the triangle associated with that bottom chord member? CD. That is CDQ. So loading joints are at C and D. Loading joints are C and D. Loading joints are at C and D. Now the thing is that what can we do? We have to actually just calculate. We can directly say that even if the loading joints are at C and D, we have only one ordinate. We have only one peak in those bottom and top chord members. Top and bottom chord members. That's in the form of AB by LH, and the peak ordinate is opposite to that of that third one. That's here the ordinate would be developed at the location of Q. At the location of Q, we are having a peak such that it's positive diagram with ordinate of A, 5A by 6A H, and that value of H is H2. Now you can also solve it by, if you say we are having two joints. If you say we are having two joints, one and two joint. Now the thing is that Then finally you have to get the ordinates also. When loading was at this point, what was the value, and when the loading was applied here, what was the value we have. And then you would get a value at this location. You would get a value of some sort of this one, and at this location you would get a linearly decreasing value such that it's some value by the similar triangles. So only critical location is actually at the point opposite to that of those two joints. That's the third joint here. So at this level. Okay. Now final is that PA. Final is that PA. Can you get for the PA? Can you get for the PA? That's vertical member. PA. So PA is this one. This is your PA having height of h1, and we have this triangle of PAC, and I need to get the force in the member PA. Can you get that? I would say loading is what you can call through type. If the loading is through type, so two ordinates. And what do you know the diagram for the vertical members? Is it some sort of xd by lh, or is it only x by l for the vertical members? D by h is for the diagonal members, but the vertical members is having only x by l. So once we got the two ordinates, one is your location A, one is your location B. I would say for this one here, the value would be at this location value would be xd by lh, but your value of x is 0. So that means ordinate is also 0. And at this location, value of x is in this direction, that is 5a. Can I say that? So I would say not that d by h, so only x by l, but your value of x is 0, so this value is 0. And on this level we have that ordinate of 5a by 6a negative. Then you join them. So this is your variation. So finally diagram is this one, 5 by 6 negative ILD for member PA. So this was the end of those tricks and all those stuff. Now we have one of the problems that first and the final problem related to those trusses we have. This is the first and the final problem we have related to those trusses. Let's take this problem and wind up this class. So we are saying that you need to draw the ILD for member 1, 2, and 3 in the deck type loading. We have deck type loading, deck type bridge truss, and your dead load is 20 kilonewton per meter. That's for the entire length, entire span. And your live load, its live load length is D, that is 7.5 meter. Live load length is D, that's 7.5 meter, and it's having intensity of that's 40 kilonewton per meter. So this is not D diagonal. This is the depth. This is that's the span of that UDL length that we have used during the derivation also. That's Z by D x by L. Okay. And one more thing is that we need to get design forces in those members. Once we got the ILD, then after that find the design forces in those members. Now we need to get the ILDs. Then after that we need to say where should we place the load such that we can get maximum force. Maximum force function. After that we can say this is your design force in the member 1, 2, 3. Now if I take that truss, what the truss looks like, how the truss looks like, I would say the variation of the truss, representation of the truss is in this way. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2. Now this is our truss, and let's say there are some support A, and here we have one more support B, and we have diagonal members also. In the form of reverse N. Let's say this one. Okay. Now the member is that our member is now 1, 2, 3 member is this one. Let's say this is our member 1. This is 1, and this is what you can call as this is 3, and this is 2. So 1, 2, 3. 1, 2, 3. Now can you get those ILDs for these three members? Can you get this ILD for these members? Let's say that total length is L equals to 6A and value of A is 4.5. So overall value is 4.5 into 3 times, that's 9 3s are 27 meter, and height of H equals to 4 meter. So you have this 4 meter, this is 4.5. So you can get the diagonal equals to 6.0208 meter, and you can get the value of D by H also, that's 1.5052. So this data we already have to get. Okay, now let's try to draw the ILD. Let's go for the first one. That's your member 1. Can you get the ILD for member 1? Top chord member. You have the member 1. So that's top chord member. And the loading is what you have. Loading is deck tap. Loading is from the top side, joints. So loading joints are these ones. These ones are your loading joints. So you have this member, one member, and its triangle associated is this one, and loading is placed at those two joints, at those two joints. But I would say directly that the peak would be developed at the third point, because member is what you have horizontal, top or bottom cut. For that we have only one peak ordinate, that's at the third joint. So that means the critical location would be at this point, critical location. So I have that ordinate, peak ordinate. So this is the diagram. Here the ordinate would be equals to AB by LH. So here the ordinate would be this is 4A from one side, 4A, 2A by 6A, height of H. And you substitute those values, you would get a value of overall final value equals to 1.5. 1.5 ordinate of 1.5. Then now I'm going to remove this part. Ordinate of 1.5, you got ordinate of 1.5. Okay, this is the case 1. That's for the member 1. Let's keep it to a side for now. So we got the member 1. Now let's talk about the second one. That's member 2. Let's talk about the member 2. Let's talk about the member 3. Let's talk about the member 3 first. I would say member 3 is bottom chord member, and loading is from the top side. And you see the triangle. Loading is applied at this point for the member 3. That means peak gets developed here, or with the peak gets developed here or here. That's the concern here. We need to see why does the peak gets developed. See, for the previous one, we said that loading was placed here and here, and I said that finally the peak gets developed at this point. So actually the peak gets developed. You have to check that at what location your peak gets developed. But because the thing is that we have one of the joints in the same line, I would say peak could have been developed at this point. Would have been developed at this point. Otherwise, you have to check all those two different loading joints, and you have to check the values there. But if you talk about this one, would the peak, because the loading is only applied at this joint, that means definitely the peak gets developed at this point, at this joint only. But for the previous one, we said your joints are two that are critical. But I said that joint peak would be developed at this location. That's because of that we say if you have these one, what you can call is two loading joints, that third one would be, if it's on the same line, the peak gets developed on that point. But for this one, you have to check that. Also, you can check that by the equation. So if I take that, I would say the peak gets developed at the mid part. You can have that by the analysis also. That's if you are good at analysis, you can do that way also. But if for the strict way, I would say load is applied at this joint for this case only, because load is applied on this only at this joint. So peak would get definitely developed at this point only. So first I would say criteria is that you check the loading, you check the what you can call as loading joints. Based on that, you decide where it should be the critical location. So main criteria should be the loading joints. Where are the loads applied? So main criteria is that loading joints. Okay. Now I would say the diagram would be for the bottom chord members. Diagram would be for the bottom chord members. Diagram is positive, and for the top chord members, diagram was negative. This was negative diagram. Bottom chord members, top chord members, and for the bottom chord members, we had positive diagram. And because of the symmetry, I would say your A and B are same, that's 3a divided by 6ah, and that value you can solve, that is equals to that value equals to 1.6875. 1.6875. 1.6875. Let's keep also this part to aside for now. Let's keep it to aside. Now we're saying what is the third condition. Now for the third one, that that member 2 vertical diagonal member 2 diagonal member 2. Let's talk about the member 2, that's diagonal member. So this is your member 2 diagonal member. So we have to see the triangles associated with that. One of the triangle is this one, and one more triangle, that's this one. And loading is applied at this joint, and loading is applied at this joint. So we have two critical locations for the diagonal member. And is it a reverse N, or is it is this in a reverse N, or is it a actual N? Can you tell me? Can you tell me, is this part, is this member inclined in a way that it's forming N type, or it's forming reverse N type? Can you tell me? If it is forming N type, that means the direction would be in this way. The direction would be in this way. But if it was reverse N, that means the direction should have been opposite of that its orientation. If the orientation is in this way and the configuration is N type, that means the direction should be in the same orientation. Starting direction should be same orientation. Now based on that, I would say, because your member 2 is having a shape of N type, it's having a shape of N type, and that means if the member is in this way, that means orientation of that would be also in this way. So starting would be in this way. Now we need to get we got the two critical locations. One is the location of this one and this one. So we have two critical locations, this and this, and up to that we have to connect the line. We have to connect the line up to that point. So let's make this part as bigger line, because we have to calculate a lot of stuff for this problem. We have to calculate a lot of stuff for this problem. Let's try to make it a bigger one. Let's try to make it a bigger one. So this is your ILE for the third member, member 2. And there is some negative value, there is some positive value, and we have that value of xd by LH. xd by LH. This value is 2 times. This value is 2a by 6a d by h. For this value, we have x from the other side. We have this value of x. And for this one, we have 3 times. From this side, we have 3 times 3a by 6a d by h. And you can solve those values. That's this value is finally this value is 0. This value is equals to 0.7526. And from this one, we would say this value is equals to 0.5017. Then you join that. Let's take the first case. Let's take the first case, that calculation for the member force for member 1. Let's go for that one. Design force for member 1. Let's keep it aside for now. And now we are taking the first one. That's it's saying that the loading is dead load and live load. We're having dead load and live load. Dead load is 20 kilonewton per meter, and total length is 27 meter. 6 times 4.5. We got the P coordinate for the member 1, and total length was 27 meter. So for the dead load, we have to place the dead load for the entire part, because dead load can't go anywhere. So dead load for the entire part. So dead load for the entire part. Now we have to place the UDL, that's live load. We have to place the live load. Live load length is only 7.5 meter. D equals to 7.5 meter with intensity of 40 kilonewton per meter. And this is your 20 kilonewton per meter intensity dead load. 20. Now we have to place it in such a way that our force that force function is maximum. So I have to place the that 7.5 meter in such a way that I would get maximum force. I have to place it such a way that if this value is z, if this value is 7.5 minus z, so I have that equation. for condition of bending moment to be maximum. We know that. And for the diagonal member, for the for the bottom and top member, it's some sort of similar to that. So for to maximize the effect, I would say that equation z by d equals to x by L. So if I use that equation, I would say what's the value of z? I can have divided by z minus x. Your value of d is equals to your value of d equals to 7.5, and that is equals to x by L. Value of x for this location is this one. This is your location of x, and you can check that value of x. That's 4 times. That's 4 times 4.5. That's 18 meter. This is 18 meter, and this is 9 meter. So value of x is 18 meter. Value of L is 27. Is that the true case we are saying? Is that true? Why we had to perform that analysis? Yeah, because the peak develops at 4a. This is equals to 4a. This length x equals to 4a, and then finally I got the value of z equals to 5 meter. That means from this side I have to place 5 meters, and from this side we have to place 2.5 meters. So finally I am going to say that if this is your diagram, if this was your diagram, I would say this length, this peak ordinate was 1.5. Peak ordinate was 1.5. Then I had to get the ordinate at this location, and we know that ordinate was same, y1 was equals to y2 during the derivation of that condition. We say that this ordinate y1 is also equals to y2. Now I got that this is 5 meter and this part is 2.5 meter. So I can say your UDL had to be placed under this area. So I would say total moment, total force F1 equals to, let's contribute because of the that dead load. Because of the dead load, area under the curve is 1 by 2, total length is 27 meter, and peak ordinate is 1.5, and you have to multiply that intensity, loading intensity, dead load intensity. Now because of the lie load, you can directly say this is 1 by 2 sum of parallel sides. We have to get this ordinate. Can you get this ordinate? If this is total 18, and you have to subtract 5, so this ordinate would be 13 by 18 into some ordinate of 1.5 yc, 13 by 18 of yc. So I would say 1 by 2 sum of parallel sides, that is 13 by 18 into 1.5 plus 1.5 ordinate. Then it's for the length of, because by the symmetry I would say y1 equals to yc, y1 equals to y2. So we then directly write it in a final way that it's for the length of 7.5. So your base is 7.5. We don't go for separate calculation then finally, because this ordinate is same as that of this one, and this ordinate is same as that of this one, and then we directly write it in this way. So let's take that, and we had to multiply that intensity of 40 kilonewton per meter. That's live load intensity. So this is your calculation for force 1. That's finally you got a value of 792.48. Because the diagram was negative for the first case, it was a top chord member. Member 1 was top chord member, so negative. Finally this amount of kilonewton compressive. So this is the design force for this member. That means for this condition given loading, you have to design this member in such a way that it should in actual case it would be having subjected to those 792 kilonewton load. It would be subjected to that amount of load. So you had to design the section in such a way you are applying a compressive load of 792 kilonewton. So accordingly you have to design the section of this member 1. So accordingly you have to design this section member 1. Now for the member 3, let's go for the member 3. We got the diagram member 3. For the member 3 we got the diagram, I think this one. Yeah, this is the diagram for the member 3. The peak ordinate was 1.6875, and for this one also you can we say the peak was developed at the midspan. Peak was developed at the midspan. Let's remove this one. I would say peak was developed at the midspan. So peak was developed at the midspan. This is 1.6875 peak. This is for the calculations of member force in the member 3, so F3. Now I would say UDL should be placed for the entire length, and if we say A equals to 13.5, or we can write X equals to 13.5 meter for this case, and I have to place the load by this symmetry. Can you say what this 7.5 meter live load, how should we place this? If I write that Z by D, Z by D equals to X by L, then I can say the Z should be 3.75 meter. So that means equally, I have to place it equally from both sides. So this is 40 kilonewton per meter, and the dead load is 20 kilonewton per meter. So I can get the ordinates here also. I can get the same ordinates, y1 equals to y2, and this ordinate would be equals to, if this is 3.75 and total is 13.5, I would say this ordinate would be 13.5 minus 3.75 divided by total length of 13.5 into this ordinate of 1.6875. This is your ordinate at this location, and same value is here also. Now if I want to get the force F3, I would say the area under the UDL 1 by 2, 27 meter, ordinate of 1.6875 into a UDL of 20 kilonewton per meter. This is because of dead load, then plus, and the diagram is positive total. So 1 by 2, sum of parallel sides, sum of those parallel sides, that's 13.5 minus 3.75 divided by 13.5, then this factor of 1.6875. So we can write it in this way, 1.6875 into that length of 7.5 meter and into that intensity of 40 kilonewton per meter. Then finally you can get the value as equals to F3 equals to minus 891.56 kilonewton. That should be positive. F3 should be positive. This is a bottom chord member. Positive diagram should be there. This is a positive value. I would take as positive value. Now for the third case. Let's go for the third case now. That's the diagram we had already. We had already that diagram. Why we kept that? Why we kept that diagram? So let's make the diagram again. Let's remove all that stuff. Let's remove all this stuff. I would say you had this diagram in this fashion. So this was your 13.5, and from the other side also you had 13.5. So this was your 13.5, and this one is your 9 meter. This is 9 meter. After that you join it. So this was 13.5 for this case of, for the calculations of F2. This was your 13.5 up to this peak, 13.5, and from the side up to the peak the length is 9.5 meter, 9 meter. That is 2A, and this was 3A, and one of the A is between these two, and the ordinate here we have calculated, and it was 0.7526, and from the side we have ordinate of 0.5017, and diagram was, this was negative diagram, this was positive diagram. Now we have two different cases here. We have to get this force in the member 3, F3. So we have two different options. See, for the UDL have to be placed for the entire length. UDL have to be placed for the entire length. This is 20 kilonewton per meter. Okay, this is the thing you have to place for it for the entire length. Now for the case of, for the, what you can call as, for the live load, that's only a length of 7.5 meter. That has to be placed in such a way, that we want that function to be maximum. So we have two different cases that we can have: V positive maximum and we have that V negative maximum. If you want that, I want shear in terms of positive, I want positive shear to be maximum, then I have to place the UDL in that part only, that positive side only. Now if I take that separately, let's take the positive side first. If I take the positive side first, then I have to calculate the force one. If I take this part, if this is 0.5017, that this was your total length of 9 meter, and we don't know this value. We need to get this value. We need to get this value such that I can place the load accordingly. Now we have to get this by the similar triangles. I would say this length, total length is A, that's 4.5 meter, and I have to get let's say that this is x length, where this is 0, neutral point. Let's say this is the length of x. I would say 0.7526 for the length of x, and from the top side we have ordinate of 0.5017 for the ordinate length of 4.5 minus x, and you can get the value of x, and x equals to 2.7 meter, and from the other side you would get 1.8 meter. 2.7, 1.8. That means this length is equals to 1.8 meter. 1.8 meter. Now the thing is that because of the UDL, you have only one option. You have to place the load for the entire part. So because of the UDL, let's calculate because of the UDL. Let's say this is 2.7, this is 1.8. Because of the UDL, you have to calculate. You have to calculate the effect for the entire length. So if I write that V1, V because of dead load, that's equals to negative and positive area summation. So I would say 1 by 2. One of the triangle is that's having ordinate of 0.7526 into length of, what is the total length it's having from the negative side, 13.5 meter plus some 2.7 meter. This is in meters. Then I have that intensity of UDL, that's 20 kilonewton per meter. This is negative area. Then we have to add positive area also. 1 by 2, 0.5017, and this length of 1.8 meter plus 9 meter, and that intensity of 20 kilonewton per meter. So you get a value of shear because of dead load. That's equals to minus 67.63 kilonewton. This is because of dead load that shear developed negative times. Now we have to contribute. Then we have to add the effect of live load also. If you want that V positive to be maximum, then I would say V positive final. If I say V positive final, that would be equals to V because of dead load plus V because of positive shear because of live load. And similarly, if I want V negative final, that would be equals to V because of dead load plus V negative because of shear because of live load. So I need to get now these two conditions. I want that V positive shear because of live load to be maximum. Let's say I have to place that total UDL of 7.5 meter with the intensity of 40 kilonewton per meter. I want to place it in such a way that I want that maximum ordinates. I want maximum area under the curve such that I can have maximum force because of that. So I had to place that. I would say I can apply that same condition. Z by D equals to X by L. X by L. Your L is 10.8. So I can get the value of Z. How much amount of Z you have to keep on this side. So Z equals to 1.25. That means from this side you have to place up to 1.25 meters. 1.25 meters. From this side you have to place 6.25 meters. And you can get the ordinate here. I would say the ordinate was total of 0.5017. It was for the length of 1.8, but I need for the length of 1.8 minus 1.25. I need for this triangle now. So accordingly you have this ordinate, and that value of ordinate would be same from this direction also. This ordinate is same as that of this one. Then I would say V positive because of live load is equals to area under the UDL 1 by 2 semi-parallel sides. I would say 0.507 is common for the parallel sides. Then this factor of 1.8 minus 1.25 divided by 1.8 plus 1 factor. Then intensity of and it was for the length of 7.5 and intensity of 40 kilonewton per meter. Or you can do separately also. You can check that, you can verify also that if you try to solve it separately for this length of 1.25, this is length of 6.25 meter, you can also get the same value. So that's equals to V positive that because of live load, that's 98.26 kilonewton positive. So I would say what is the V final because of positive? V final positive, that's initially we had dead load minus 67.63 because of dead load minus 67.63, and I would add that positive 98.28. So minus times that's positive plus 30.53. This is a positive value that you got. Final V positive shear force. V for positive shear force. That's final design force for the member. If you want to account only for positive shear force, positive force, compressive This is not shear force. We are saying this is that compressive force. If it is positive, we say this is tensile, and negative compressive. Now second case is that what you can call as we need to calculate force because of negative side area. Let's take that negative area. We are going to take that negative area. So let's remove all that part. Let's remove all of the data. Let's remove all of the data. Let's have this only. I would say this was the length of 13.5. After that we have one more 1 point some length was also there, 2.7 meter, and we have this negative triangle. Then I need to place the UDL in such a way that we have the maximum effect. So I would be placing in such a way that if I write that this is some value of if the total length is d equals to 7.5, and I'm saying that this value is x, this part is x up to the center, I would say value of x can be calculated by this equation. That's equals to, what is the length we have up to this point? What is the length we have this? Now we represent this one by z. We represent it by z. What is the length of x we have up to this point? That's 13.5 divided by total length. What is the total length we have? This is the total length. That's 13.5 plus 2.7. So you can get the that z value equals to 6.25. That means from the other side you have the value of now if this value is 6.25, so this is 6.25 meters. From the other side it would be 1.25 meter. Then accordingly you can get the ordinates. You can calculate the ordinates also. So here we can write the ordinate. If this is 6.25 for the length of, I would say the ordinate for this triangle, this ordinate would be 0.7526, and it was for the length of 13.5 meter, but I need for the length of 13.5 minus 6.25 meter. So you can get the ordinate. Then if I write that V negative final, I would say what is that equals to? V negative because of live load. That's area under the curve 1/2, sum of parallel sides 0.7526, and make sure that it's all entire negative. 1/2 is that ordinate of 0.7526. If you keep it common, I would write 1 plus that finally 13.5 minus 6.25 divided by 13.5. Then after that we have the length of 7.5 meter of that live load, then intensity of 40 kilonewton per meter. So that value is equals to 175.46, that's negative kilonewton. Now if I say what is the total effect because of that negative, I would say in terms of negative, if you want to calculate V negative 2, or we can say negative force calculations for the member force 2, that's equals to minus 67.73 plus minus 175.46. That's final value of minus 243. Some 4919 some, let's say some let's take any value 5. Let's take any value, general value, that this is some value of V. So design force, which one should you take that design force finally? One of the forces you got as positive 30 and one of the values you got as negative. So it means that in the tensile force you have to design the member in tension that it should have design strength more than, it should take more than, it should have this much amount of force. It can take this much amount of force, and in the compressive forces it should take this much amount of force. So this is the final problem. So thank you for watching our series, and this was the end of the influence line diagrams. Thank you for watching.